First we do a mic check.
It works.
Yeah. And then everybody goes quiet. Welcome everybody to RustNL 2024. I'm your MC for today. My name is Alex Band. I work at Anonet Labs, and I do this together with Adolfo.
Yes.
Hi.
Yeah, I'm Adolfo. I work as an independent consultant on open source Rust crates and systems programming projects.
You really had to think about what you do.
Yeah.
Yeah. No, I don't know what I do. It's a miracle they asked me. Apparently this was a success last year. And I said, are you sure you don't want somebody from the Rust community to do this?
You are from the Rust community.
I am from the Rust community. Sorry. Imposter syndrome, I'm very sorry. No, this is going to be great. Yeah, where do we start? It's the yellow t-shirts, right? Okay, so everybody who organizes today, and it's a lot of volunteers who made this event happen, they're all wearing a yellow t-shirt. Give them a big round of applause. If you need anything, find one of them and they will be able to help you out. If you signed up for a workshop, that is not here. That is next door in Chemistry and Chaos, of Chemie en
It's
Chaos.
in lab.
Yes, and that is next door. This is also where basically everything else is that is not a presentation here. So also lunch will be served there, this is where the breaks are, and it's a beautiful day outside, finally. I don't know what happened. It's Netherlands and it's nice weather.
Someone ordered it.
Yeah, so we could have lunch outside or in one of those areas over there. That's the other thing I wanted to say. We have a code of conduct. And the Rust code of conduct and the code of conduct for this particular event, super important to us. So please make a note of it, read it, and please adhere to it. So the inclusiveness of this community is one of the founding pillars of what makes it beautiful. So please keep it in mind. Anything else? Yes, this event is live streamed, so no pressure. Right? Yeah. It's live streamed to Vimeo, and then afterwards it'll be published also on YouTube. This is scheduled for today, and I would want to thank all of the sponsors, but I don't know all of them by heart, and I'm going to leave one out, and probably the people who do the audio-visual, they have it on a slide somewhere, but, you know, I won't be able to tell you. Anyway, see, there we are. FutureWide Technologies, Hyperswitch, Tandem Drive, Tweede Golf, MakePad, Baseflow, Technolution, Main Matter, One Variable, and the Rust Foundation. Thank you to these sponsors for making this event possible. Last year we thought, you know, let's do something a little bit small to see if this works. And now look what a giant event we have organized. 2 days, and we're massively looking forward to it.
Yep. So, will you introduce the first speaker, or is there anything else you want to say?
No, yeah, I wanted to say, but apparently all of my co-hosts work on Russells. That is a thing. Or have at some point worked on Russells. Yeah. It's a thing. It's nice.
Well, maybe.
Yeah. Okay. Well, the first speaker then is Rick Arendt. Yeah. And let's see if he's going to recompile the IDE whilst doing a live demo.
Like last year.
Just like last year. Thank you very much.
All right. Welcome everybody. I'm waiting for my my screen. Let's hope that works. Yeah, there we go. And as you can see, we're going to start with cargo clean. There we go. Just so you know, I'm serious. Let's see. I did make my build command a shell script, so I don't have to type it. But since last year, we have, of course, written a year of code, and Apple has made faster CPUs. So that turns out that our build time is pretty much the same as last year. So, yes. 8.5 seconds, clean build with all dependencies. I mean, that's nice, right? This is why you want a new MacBook. I mean, yeah, tell your boss, and like, yeah, it's useful. So, let me boot up my slides. And I was honest, everything is going to be compiled from scratch whilst we do this. There we go. These are my slides in the IDE. So, hello RustNL. Visual application design in Rust. Yeah, when I decided to make this talk, or propose the talk, I always make some lofty goal, and then I'll see how far I get. So, you know, we got pretty far, but you'll see how far we got. We're building MakePad, and we're trying to bring back what we lost when we lost Delphi and VB. Not that I ever liked Delphi and VB as programming languages, because they were slow. I was a C++ guy, so I liked Visual C++, which had a dialogue editor, and that thing was absolutely fantastic to me, because that meant that I could prototype my ideas visually before I started to write code. The UIs looked terrible, but were very functional, because I could make buttons for everything. And so I want to bring that back, but for a new language, in this case Rust, which is fast as C++, and you will not suffer null pointers, and all those horrible things, memory corruption. So we're building a new IDE and a new design tool. The idea is to fuse the visual design. I mean, we're not in 1995 anymore, so we can't build a dialogue editor and call it a product. We have to go, okay, it has to at least do what Figma does, right? Or it has to be very visually expressive. It has to be very fast. And run everywhere. But why I want to do this is because I love having fun with code, right? This is why I started programming on an MSX, where you had circle and beep and play, and you could make it make sounds. And that was magic to me, right? That's what I wanted. Except as time passed, this simple way of interacting with a computer became harder and harder and harder, until the point where when you want to play a sound, you're like, no, not today, you know, maybe tomorrow. So that is part of the mission of what we're trying to build, is that all these basic APIs like sound and networking and graphics are as easy as I can make it in Rust, which has limitations, but it's not going to be basic, but it has an idea. As you know, I focus very much on compile time, because Rust has kind of a bad name, especially among C++ developers, that it's very slow to compile. I don't think Rust compiles slow at all. I think we're just loading it up with too much stuff. Right? We're just adding too many dependencies that are completely thrown out, or like 99% thrown out. Like an example is the crate that Microsoft made, Windows RS. If you download that thing, no, it's great. I'm very, very happy that they made it. It's an amazing piece of engineering. They've wrapped their entire platform in generated Rust code that is actually Rust native. It feels Rust native. It iterators, async, everything works. That's amazing. The problem is that they just wholesale converted the entire platform API, so it's 360 megabytes of Rust, which is roughly modularized. So if you want to access a single function call from the Windows API to do something for your command line tool, everybody is going to just download all that, and then it churns through it, and then, I don't know, it takes like 45 seconds or something. Long time, but it's wasted. So for MakePad, what I did is I wrote a little regex engine kind of thing that just stripped Windows RS of everything that I didn't use. And so it's not a very nice tool. I wish that Microsoft would properly do this. But if you just look at the imports you use and then generate the platform from it, I was able for MakePad to run on Windows with all sorts of stuff, audio, video, windowing, clipboard, all that stuff. 365 megabytes or something went down to 1 megabyte. That's how much I used of the platform API. So if we can choose to generate these things in future, instead of like, you know, whole hog converting it, then you get these 8-second compile times, also on Windows, also on Linux. But yeah, we have a strong focus on compile time. I'll get back to that in a bit. But they asked me, or they told me that we have side screens here. And I was like, side screens? Yeah, what do you want to do with the side screens? So I was like, okay, how about Apple TVs? So yeah, there's my Apple TV. Here we go. So this is tricky, right? I'm going to now deploy a Rust application to my Apple TVs. And it's using all of the signature stuff of Apple. And this is really kind of tedious because it phones home. It asks the server if it can sign a binary, and only then will it run on your Apple TV. So let's see if that actually works. Oh, deploy. Not deploy. Oh, all right. So of course this is the Ironfish thing, the synthesizer that I showed last year as well. I'll show it in a bit too. I can also compile so this is the fractal zoom on my main machine. Let's compile it to the Apple TVs. There we go. I would say it's fun to figure this out, but you know, this is the part where you're like, okay, I do for my job. I get to have the fun later. So here we have the fractal zoomer, and this is MakePad Studio that I'm showing. I'll go into more in depth. This is what we're building essentially. This is the IDE. This is the Visual Basic that we're building. And here's the Mandelbrot fractal shader. MakePad is built on shaders. All of the UI is styled with shaders, but not in a like shader toy kind of way, but more in like every button is a rectangle and it runs a little shader program just for that button, right? I'm not drawing everything in a giant shader. That is horrendously inefficient. But look, I can now live code shaders on my Apple TVs, right? This is one of those things that I've been wanting to do for so long. Because the GPUs in these Apple TVs are really amazing. They're high-end phone SoCs that are in there, and you get an actual decent GPU for $150 or something. So it's an amazing device, but getting that as accessible as this, because I have projectors at home and I have these devices, and I was always like, why can't I live code a shader on that thing? Well, now you can. Because Apple TVs don't come with a web browser. Apple just threw the web browser off the platform. You don't have a web browser. So you cannot open Safari and do some WebGL thing. You have to actually do all this work and have it run on Metal. So this is all running on Metal and it's transpiling. It has a WebSocket connection to the IDE. So all of the applications on all devices and platforms that we support run on, not Android today. I'm not going to do that. So let me show you. Here is the WebAssembly build of that fractal zoom. Let's make a WebAssembly build. Let's see if the WebAssembly build wants to do anything. As I showed you, I did cargo clean, so I have time to drink some water. Okay, let's see. Did we build it? Yeah. It doesn't take long either. So here's the fractal zoomer in a browser, but because I use WebSockets as the communications protocol, when I change this shader, it should just also work in the browser. So you can live code UIs across all of your devices at once. Note the UI DSL, not the code. The code is, of course, compiled using Rust, and that is a little bit more annoying. I'll show you what that means. Okay, let's turn off WebAssembly. So a concept in MakePad Studio that I really like, that I haven't seen very much elsewhere, is that you don't build, you turn a build on, right? A build is always on. So when you change code, it rebuilds automatically. So you just turn it on, and then it runs, and when you change the code, it just rebuilds it. So when I do Studio Release, now it's running inside MakePad Studio. This is running on a cross-process texture. That was really hairy to build, especially cross-platform. It's a little bit browser technology that you have essentially a child process that is completely isolated. GPU is running in the child process, so your operating system can, if you crash this shader, my IDE will survive it, which is not something that I have seen possible in a web browser because it has a GPU process, so you're going to crash the GPU process. Here, that's not the case, which is something that I really missed if you're building a real tool. So here's the fractal zoomer in the IDE. And now, if I put my cursor here, I'm not going to change the code. I'm just going to make it recompile. If I press space, okay, let me close my slide so it doesn't flicker. If I press space, you see that the application fades out a little bit and then restarts, right? This is as smooth as I can make live coding in Rust, right? You have to rebuild it, and it has to restart the application. You can serialize the state to disk and reload it after. That's something that we're working on. Like if you have an application model that supports that, then you can have a much more live experience because the state is serialized and reloaded and represented. But personally, I find this completely acceptable way of programming. Like if I take, I mean, it's not a very pretty one, but like if I take the simple example, yeah, we'll show that in a bit. Files. Simple app. No, not this one. This one. I abuse my example sometimes a bit to test stuff, so there's a lot of stuff commented out that has nothing to do with simple. So I click on Hello World, and it sends a message. So all of the logging is also done through the WebSocket. So if I have a phone, if I have a TV, if I have a web browser, I get all my logs in the IDE via the same route as that I update the live coding. But here you see, where's my code that prints it? It says button clicked. So, right? It's I'm sorry that the UI is changing structure. But that's because of the feature I'm going to show in a little bit, which is the new design environment. So let me make it so that it doesn't bother me too much. Come on, tab. Go there. Right. So let's run it. The recompile cycle that I have with this feels to me almost like live coding, right? 1 second. That's okay. I think that's fine. And this is about as good as I'm going to make it with Rust. And with styling, so the reason that I separated the live coding for the UI and Rust is that code you usually think about a little longer, and it has many more failure states as you type it, right? So hot coding is fun if you have a really expensive startup cycle, like with a game engine or something that needs to do a lot of resources, and then you want that hot loading. But for applications and applications that we're building, like an IDE, it's also fine. You know, I can live code that as well. So here I can open MakePad Studio. In MakePad Studio, I've been developing MakePad Studio and MakePad Studio for quite a while now, and this is my developer cycle. As I go to Studio, I go to App, and then I change a bit of code. 1, 2, that's it. That's my iteration speed for the IDE. And if I change something horribly far down in my library, like I changed the platform abstraction crate, right? This is the platform abstraction crate. 1, 2, 3, 4, 5. Yeah, that's it. That's the worst I'm going to get in terms of iteration cycle. So Rust isn't slow. Rust is actually pretty fast, as long as you have a fast computer. This is an M3. I do like to, because this is the developer cycle that I want. I'm not ashamed to use a fast machine myself, because I'm already putting so much effort into making it as fast as possible. If you have a slow machine, I already did my best. It's not going to get any better. So I afford myself a fast computer, because that's one of the things, right? If you want to write fast code, get a slow computer. No. I also have to live, right? All right, let's get back to the slides. So yeah, the side screens are now showing something from 1980, right? This is not today anymore. Today we have other ways to play with computers, especially AI. This is even more complicated. I brought my own 4090 render machine here. So, okay, here we go again. Let's see. I'm going to first deploy the Stable Diffusion XL viewer to my Apple TV. Let's see. So, when you're playing with images, and when I had this AI image generator, I wanted to show it on my projectors, but I don't want to run a virtual desktop windowing, whatever cloud-based screen sharing thing. I just wanted to send the PNG over my local network via WebSocket to, yeah, there we go. See, I even made the logo work. Before I did this, hold on, I was doing, no, not widgets. Experiments. Experiments is where I put all my stuff that you shouldn't look at, by the way, in my repo. It's not an example. Examples are slightly more curated. Experiments are just a thing so I don't have to have multiple Git repos. I don't like Git, so. Let's see, SDXL, remote. So I was trying to put that logo in the corner of the screen. So I was just like maneuvering it like this by just live editing. I was like, one of those moments where you're like, this is the moment I built everything for, putting the logo in the corner, right? All right, so so we have the Stable Diffusion thing now. I think it's now spamming my PC to connect to a WebSocket. Now we're going to run Stable Diffusion UI. This is another thing that I built in MakePad Studio. I'm gonna actually start the thing here because, as I said, MakePad Studio tries to live reload everything, and I'm going to continue, but the side screens are going to keep doing AI, so I want to run it separately. All of our build stuff is working via Cargo. All of the fancy build stuff like WebAssembly, Android, tvOS uses MakePad, Cargo MakePad. It's a Cargo extension. So yeah, we're rolling a lot of the build tooling in there. Hold on, let me see if let me say. So, say hi. Okay, this is Llama 3. So, this is an AI image generator. So, bright, sunny day, okay. And then we're going to render it, and we're going to randomize the seed. Let's see if it's working. That would be nice if it's working. There we go. Oh, right. That's an artistic impression of you. I don't think well, whatever, This is the thing. This is an AI model, and it doesn't have much boundaries, so if any of the content is questionable, wasn't me. So a bright sunny day, right? Now we have a nice bright sunny day. But the thing is, if you're prompting in a social setting with an AI, this is a thing for parties, right? You just have people typing and then projecting it on walls, so you can play with an AI generator in fractals, intricate, colorful. But this is very tiring because you have to be creative and you're too lazy to be creative. So it's like, what if we plug a text model onto this so you can go, okay, I'm bored, just do something, right? And so I thought, okay, why don't we do Llama? So describe yourself visually. And then it comes up with something. Oh, it didn't give yourself an identity. So you can talk to the AI about the prompt. There we go. Let's see what... a bot. I don't think... well, let's start over. Trim, clear. Oh, in the style of a cartoon. Anyway, this is endlessly fun. I just wanted to show this as like This is an application that I built in probably about a week in MakePad, because I was trying out, okay, how do we do networking? How do we do async? How do we build a form UI? How do we, how do I build a chat with an... I don't know. Yeah, okay. I'm happy that it's actually staying within the boundaries of acceptable, because you never know with this thing, right? But we're gonna, let's, I don't know, I guess this is a nice and distracting set of pictures for the side screen. Let's keep that running. So, let's get to my slides. So, a nice thing now is that hopefully the AI will just keep going, and I can use my IDE. So, oh yeah, I was going to show that as well. I have a camera input. Oh, this actually might be a really cool one to fade. So you can feed the camera from your webcam into the AI, and then the denoise is sort of like the blend between the camera input and the AI. So let's see what it does at denoise 50. Let's see. Okay. All right. I think it thinks that. Well, I mean, you can see the reference. So this is a little bit tricky, by the way. I'm going into dangerous territory now. But this is one of the best party tricks ever. I did this at a party, and at some point I was like, okay, I gave you the universe, right? And what do people do? They make themselves look like pop stars. Like, okay, all right, fine. But yeah, so essentially it becomes a Snapchat filter. Humans. So I'm not building this alone. I'm building this with my design co-founder, Sebastian, and Eddie Bruel for the hard things. That, I'm just like, Eddie, can you figure this out? And he can do it. It's great, because I like to go fast, and he does things like he fuzz tests, right? Like, okay, I really want to do, yeah, okay. And then something comes out that is so rock solid that I never have to ask him anything ever again about it. So that's the cool thing about our cooperation with Rust, is that when he makes something, he gives it to me, I can refactor his code without asking him a single question. Right? This is a completely new experience for me when working together with other people on the same code base. And also the good thing about Eddie is that he writes code so thoroughly and slowly that it is extremely condensed. I'll bring up his latest achievement in a bit. So I want to show a little bit MakePad Studio. This is the main, how much time do I have? Because I meander a lot. Okay. 10 minutes? All right. So MakePad Studio, that's the thing that we're building, right? I just shifted the designer out of the way. Sorry if the screen's a little bit small. I have a 57-inch 8K widescreen monitor, and I stretched the IDE all the way like this, and then I have 3 code editors, and a design tool, and a running application, like on one wall, running at 120 hertz. And I'm like, okay, if you're building a future tool and this is the way it's going to be, then yeah, I'm pretty happy with that. So where's my design? Okay, there's the scene. It's the wrong way around. So let's change that a little bit. Ironfish, no. Okay, I'm going to restart it. Ironfish, scene, design. Yeah. So this is the Ironfish demo. We even added some presets now, so I don't have to difficult stuff, or like arpeggiated. It's so much fun. Every time I open this, I spend like 15 minutes playing with it. And then, but this is not a real application. This is just a test for me to see if I actually have a visual design tool. This is now, this is the graph of the UI tree in the running application. And the way I built this, because that was a long-running engineering problem, like, okay, how do you build this visual? Where do you put the visual designer? Do you run it in the IDE process, or do you run it in the user process? And if you run it in the IDE process, you run into the problem that Visual Studio had, at least when I was playing with it, I don't know, 15 years ago, with .NET, was that if you wanted to have user components in your visual designer, it had to load the user assemblies in the IDE, which is, of course, not very nice if you have custom components. For instance, this piano, that's not in my general widget kit, that's in the application. So, but you still want to be able to visually design it. So what I made is that the application is running in a texture, on a cross-process texture, but the designer also opens extra cross-process texture windows in the IDE. So it doesn't look like it's in the application, but this process, these things are in the application. Oh, I didn't want to show mobile. I wanted to show desktop. Also, I think that color picker is a bit in the way in my small screen. So because the designer is running in the user process, I can actually live edit the designer in the IDE, which is also very nice, especially if that's the main thing you're doing right now. Hold on. My editor is not really complete yet. Designer view, designer container, designer toolbox. I think it's the designer toolbox. Yeah, I need some better code folding. No. Where's my color picker? Also, I don't have search yet. It's a great anti-dementia thing, not having search in your IDE. Yeah, absolutely. As an aging developer, I recognize that that is important. Button flat. So yeah, otherwise I would be able to search it. But this is also a nice little look at the DSL for the designer. The designer is built in the same structure as we're building the design thing with. Where's my color picker? Here's my color picker, right. So if I comment out my color picker, it goes away. Cool. But I wanted the whole rectangle to go away. Okay. So I'm going to comment this out. I hope the indenting is all right. Oh, Sebastian put a lot of stuff in there. Oh, still there. Wait, I need to go one up. Oh. Okay, this is why I'm like, okay, you know, the IDE is nice, but I need some new features like, you know, group comment and all these things. Are we going to go away now? My comment is nested. Oh, did I break it? Hold on. Gonna restart it. Are we restarting? Okay. Maybe I pushed the demo gods a little too far now. Well, anyway, we're going to do it without the color picker. I'm just going to make it a little bigger. So this is the design canvas. This is the design canvas. And as you can see, it is essentially a splat out of all the components in the UI. It functions very much like a Figma design document of the application. So you can see all the instances of the components. By the way, this is also a feature that I'm very happy with. We now have on-demand SDF generation, thanks to Eddie B., not Eddie Bruel. He implemented an on-demand SDF font generator, and that is quite novel. It is invented by the guy from acco.net, you can look it up. SDF used to be very hard to generate because you had to generate a massive picture of 1K by 1K and then downscale it. But he made a separatable algorithm so that you can actually, in real time, on demand, generate SDFs for your 16,000 character internationalized font. And therefore, we now have a fully flexible floating point zooming of our entire UI. A lot of the UI that you see here is just the recent developments of Sebastian designing it. The goal of this tool is to be his primary workflow. And I will not accept anything less. Just like this IDE is supposed to be my primary workflow, and if it isn't, what am I building, right? It's like if you can't make a tool your primary workflow, then you didn't build a tool. You built a toy. And even though I like toys, I still would like a good tool to build toys. I'm a bit sad about. It's just too much stuff on my screen now. Let's see. MakePad Studio. So the MakePad UI framework that I was scrolling through a little bit, it has a slight look like HTML. It's a prototypically inherited object structure that is in linear memory. So it's not a tree. It doesn't have pointers. It's a single vector. So that means that I can do very fast expansion and do the inheritance in the document. So it's like JavaScript, except it's done at initialization time. And then I can instance all these components from that data structure. And instead of the React or reactive model where you write code and interleave code with UI, it is using a query model. Because as you can see here, the whole UI needs to remain a document that is editable in a visual tool, right? The whole UI needs to be essentially a serialized file of a design tool. Otherwise, it will never be able to keep the designer there. If you start mixing code in there, it's going to break the designer, and I have no idea how to do that. And actually, almost nobody has. That's why we don't have good design tools or not very functioning design tools for a lot of the UI stuff out there. So this is a hard choice. No code in your design structure. Okay, what can you do then? The only thing you can do is queries. So jQuery. It was actually a decent idea to prod at trees with, you know, and this is why all of the UI button click connectivity between the Rust code and our DSL is using queries. And to me, I actually find that pretty nice. Let me show a single example. This is why you need a 57-inch screen for your design tool. Although you can do tab switching, but that is not as nice. Simple app. Here you see the query. So I tried to condense the query in Rust as much as I could, but you say UI.button. This is an extension trait that queries for buttons with this query, and then you can check if it was clicked. And the great thing is that this is not a closure, is that closures are actually not so nice in Rust, because you have to deal with the mutability of your data. If you can make it a single if, it's just a top-down flow, and I have zero data locking problems. Okay, I have some more to show you. Anyway, my idea for the future of this is a new idea. Uh-oh. Oh, this is positive. Bright blue sky. This is like, what is it from that movie? You Are All Bugs? Series. Anyway, so tool-assisted instancing. So composition in UI is actually... okay, anyway, this is maybe I'm going to stop this right now. There we go. We're going to look at a blue sky. Nice Windows background. 1 minute. So tool-assisted instancing is the idea that instead of using coding inheritance, maybe we can use composition from a code generation point of view, like a Git structure. So you can clone something, but because it can just compare the clone, you can solve the inheritance of these things without the fragile base class problem. Oh, and Eddie's achievement is that he built a WASM engine called Stitch to minimize our compile time. Because I was like, let's use a WASM engine for syntax highlighting so we can load syntax highlighters. And then MakePad became 25% of the build time, and that's just not acceptable. So Eddie, 6 months ago, decided to build a WASM engine, and he finished it recently. It's the fastest WASM interpreter in the world right now, I think, slightly faster than WASM 3, written in Rust, and it's spec compliant and fuzz tested. So yeah, I had a demo for embedded Rust, because we're going to do a workshop this afternoon. Let's see if I can run this thing. This is another big if. This is an ESP32 RISC-V that is running Rust, and I'm going to start it up. Let's see, ESP car. Oh, there we go. Come on, ESP, connect to the Wi-Fi already. Oh wait, maybe it already did. Maybe I don't send key presses in my IDE. There you go. Yeah, so that's embedded Rust today at 2. And you get a free dual microcontroller, Raspberry Pi RISC-V to play with. And we're going to build a connectionless chat room with a MakePad UI. So, yeah, that's it. Thank you.
Yeah. And now, of course, it's time for questions. Somebody will be walking around with a mic. Can you wave your hand? We say, Lucas. There we go. That's the first question over there.
What shading language were you writing your shaders in for the Mandelbrot thing? Looked like Rust, but...
Yeah, it's essentially a type inference GLSL that looks a little bit like Rust. I just decided to make my own syntax because it is something that I wanted to be easy for UI. So here, for instance, you see that we have structs with methods in shaders, and we have a module system. And so you can make a standard library that has, for instance, SDF primitives that you can just draw like it is a canvas, like circle. But underneath, it's doing all the math, and it's using a stateful struct. But having my own syntax allowed me to, as I say, unsuck it a little bit. Because GLSL is really not a modern language in terms of modules, in terms of all the things that Rust brings, type inferencing, like this type inferences. I mean, Eddie built a type inferencer. This is why Eddie does the hard things. Like, Eddie, could you build me? I built a type inferencer once, but it wasn't as good as his. So.
Nice. Anyone else have a question? Yes, all the way in the back.
Hello. So I tried MakePad a year ago, and at the time I can say it was heavy in development I seen. And what I was surprised the most about is that I had to pass the redraw calls everywhere. Now I look at the tutorial. Oh, no. Congratulations on making the tutorial. It's cool. And the redraw calls still exist, and I still need to pass them down. So what's up with that? Why do you have to do that?
Why do you have to redraw?
No, not redraw, but explicitly pass redraw events to the widgets from parent widgets.
Oh, well, that's because MakePad, might have mentioned that, should have mentioned that, is a hybrid retained immediate mode API. So one of the problems with UI rendering, UI frameworks, is that they always assume one or the other. Either it's immediate mode, like eGUI or ImGUI, or it's fully retained, like browser DOMs. But as you build widgets, like as you build this code editor, right, or design tools or log views that want to have millions and millions, this log view can process, you can blast at it in a dense for loop, you can print, and it doesn't crash. Because all of these widgets are essentially immediate modes. They just have a viewport on the data and they draw it in that draw call of that widget. But the widgets can be combined in retained mode trees. So you can choose whether or not you want to use the retained mode structure or the immediate mode structure, depending on your use case. And I think that is absolutely required if you want to build something like this. Because if you have to do the code editor in a retained mode API, we tried, right, with Cloud9. I'm not going to ever do that again. You want immediate mode drawing APIs for actually most of the complex widgets that you do. But you still want to, for instance, you can have an immediate mode list, right? So there's data coming in and you draw the list, but then you can instance the retained mode substructures out of the DSL, right? So you can just mix and match.
Next question over there.
So this is a question from the live stream. In terms of compilation time improvements, do you think that Cargo needs more attention in this respect, or Rust-C, for example, in relation to features and dependencies?
I think if you want to have fast build time, you need to change your attitude of how you deal with dependencies. So, no left pad, I'm sorry. No random convenience libraries just to make something green in your console. You know how to write ANSI. You don't need a library for that. And the other thing is we need to change the way we do platform import libraries, like the Windows RS example. But BindGen is completely architected the wrong way around. For instance, I've written all of the Linux stuff, like ALSA and Pulse, and this is the fun, not so fun part of doing this. And what I did is I would run BindGen, open that in an editor, get the whole 100,000 lines of that header, and then just see what I needed, and just copy that into my file. And on average, I was left with about 3% of the code that BindGen generated. So the whole syscrate thing we have in the Rust ecosystem just needs to go. It needs to change around. BindGen needs to generate sys modules, so that because Rust does it just fine with C, extern C, and it links automatically. So there's no problem whatsoever. We just need to change how we do that. And and I hope that foundational crates just start shedding their dependencies. Just like the WASM engine, all of a sudden we were like a quarter of the build time, and I had to lose my co-founder for 6 months to build a WASM engine that builds in 1 second. It's 15,000 lines of code. Or actually, it is in MakePad Studio. That 8 seconds includes the WASM engine. I didn't even notice it because it's at the end of the pipeline, so I had plenty of cores left, so it just vanishes in our build time right now. That's an approach. I think that's a cultural change. If you want, I'm not saying everybody should. I want it, and that's why I cannot use very many things from the Rust ecosystem, because everybody just piles on stuff. Like, for instance, I wanted to use OpenSSL for a WebSocket, and I was like, on Linux, okay, OpenSSL crate. And that thing that rolls in sin and quote, which I don't want in my code base, because it takes a long time to compile. For a proc macro for documentation in the, okay, all right, I'll have to do OpenSSL the way I did all the ALSA things as well, which I really don't want to do. And I wish that the ecosystem would do that out of their own ideas, but yeah. Cargo is not the problem, Rust is not the problem, it's us.
Now, based on that, that's a good closer actually. But does somebody have a question or a comment based on that? Yeah, see, I thought all of the hands were going to go up now, but okay. Last question, there in the back.
Okay, so you've already answered the question in one direction. So you said why you kind of don't want to use other people's libraries, but have you thought about like encouraging people to use your libraries, making them modular so that other people can use them?
So MakePad is essentially a giant tree of 50 crates that we wrote ourselves. But my goal is to build Visual Basic in Rust or whatever. That's my goal, right? My goal is not to maintain 1 million crates as a maintainer of that crate, and that's my thing in life. I don't, my job is to build this product, this tool. So in that sense, when I make my own crate, I make it do exactly what I want, and I'm not necessarily super interested in supporting that for everybody's use case, because inevitably that's going to weigh it down. This is why I'm saying like the platform crates should just be generated on demand as you use it. That already cuts out a huge amount of community crates that are no longer needed. Some crates that we made, like we have the regex engine that Eddie built last year, because otherwise he wouldn't use the editor. He was like, I need regex. I'm like, okay, guess what you get to make then? A regex engine, because the regex engine we had didn't compile fast enough, I thought. So he built a regex engine. It's almost in there now. But those kinds of crates, like the things that Eddie built, I think are absolutely, like the WASM engine, absolutely useful for the entire ecosystem. But I would not recommend using some of the things I wrote in there. Not all, but like some of the things I wrote in there. So, yeah.
All right. Well, thank you very much, Rick Arendt. Of course, a little gift for you.
Thank you.
Cheers.
All right. So up next we have Michael Melchior, who works at Airbus Defence and Space as a software specialist, onboard software specialist. He has experience doing real-time systems, and he's now leading an effort to get Rust into space, funded by the European Space Agency. Anything else? Well, the title already there. So a warm applause for him, and go ahead.
Thank you. My name is Michael Melchior, as was just said. I basically have done the introduction. Thank you. I've been programming data-intensive real-time software for more than 15 years in various fields, the railway, the radar, and the space industry. I started as a professional software engineer in 2008. At the same time, this book was first published. So the art of multiprocessor programming. And in the early years of my career, I witnessed and participated in the adoption of multi-core processing targets in the industry. And I think that the title of this book is quite accurate, especially at the time, given the tools that were available to us. You notice it's art, it's not science, it's not engineering, it's art. And when you're dealing with real-time, sometimes safety-critical software, being involved in art is not a really good sign or very comfortable position. So this initial exposure I had to the topic followed me throughout my career, and every time I joined a team, I became sort of the multi-core artist in that team. And with that background, it was only natural that I became interested in Rust. So I discovered Rust in 2014 and tried to bring it to my work ever since. And I succeeded in 2022. So I've known pain, but I'm persistent. So the goal of this talk is to share with you why my team is interested in using Rust and what we did to build our case for the adoption of Rust in our industry. So in this talk, you won't be saying any fancy, complicated, advanced Rust. We are more in the baby steps phase, but at least as far as I'm concerned, that's okay, because the first step are usually the most difficult to take. So first, I need to give you a bit of information of the context when you're developing software for satellites. Space first. So satellites operate in space, obviously. Space is a very hostile operating environment. The satellite is subjected to radiation, cosmic particles, electromagnetic fields, huge temperature differences. Secondly, space is very expensive to reach. It literally costs millions to just send a washing machine, a trash can in space. So when we design a satellite, the most critical budget we need to satisfy is called SWAP: size, weight, and power. So for a given feature scope attached to a satellite, we need to make it as small, light, and energy efficient as humanly possible. So to satisfy those two constraints, traditionally in the space industry, we've been using very specialized equipment. We call them radiation hardened. And if you want, what you need to keep in mind about that hardware is that it's both extremely expensive and does not deliver a lot. So it's, for example, at the start of the industry, memories were a few kilobytes big. Processors were extremely slow, up to 20 times slower than their counterpart on the ground. And yes, communication links were also extremely slow. So on the right here, you have a breakdown of a typical satellite. In the center here, you have the central processor. That's where most of the onboard software is being executed. You can see that so one of the first role of the onboard software is to manage and control all the equipment on the satellite. So for example, you have on the top solar arrays and batteries to generate and store the power. You have on the right sensors and actuators. So that's for controlling the satellite attitude. So typical actuators, you can have thrusters, you can have reaction wheels, for example. And then on the left, you have antennas, which allows communication with the ground. So far, everything I've described is responsible for the possibility and the continuity of flight. Now you need something else to generate scientific or business value. And for that, we have the platform accommodates what we call payloads that are here on the bottom. And payloads are already also have a breakdown for themselves. And we also, they also have on-board software embedded. And so we also need to manage the payload. For example, payloads host instruments. So for Earth observation satellite, this might be some really complicated, expensive camera. And the on-board software is in charge of triggering shots, storing the data until we are in range of an antenna, and downlink the data to the ground. The other role that is often underestimated is linked to the antennas there. Satellites are quite far from us, so they are remotely operated. And we need, the onboard software needs to provide everything needed to support remote operations. And this includes supporting investigation in case of failure. The software will only tell to the ground what we plan for. And if it's not sufficient to investigate issues, we're in a big trouble. Okay, so on-board software development, so at Airbus Defence and Space, at least in Toulouse, we develop mainly in C. Some of the functions allocated to advanced software are critical for the satellite or the mission. So that's why we say that on-board software is real-time, is a real-time software. So what this means is that there are some critical functions that needs to be executed cyclically to monitor the satellite, and they have deadlines associated to each function. And those deadlines must be met whatever the situation. Otherwise, we risk losing the satellite or the mission. And secondly, it's embedded software. As I said, we use specific hardware with limited resources, and we need to achieve all of that in a very limited budget. And the last point is we control very specialized hardware, I would say peculiar hardware. Each of the equipment we have has specific operating modes, and for all equipment, we need to guarantee at any given time that the operating mode of each equipment is compatible with its operating constraints. And lastly, the satellite is subjected to a lot of punishment, so it means that the hardware do fail, and that's the role of the onboard software to adapt. We have to reprogram it. For example, if a network link is broken, we need to program a backup route. So the consequence of those constraints is that there's a really high quality bar that needs to be met before onboard software is deemed flyworthy. In Europe, we have what we call the ECSS, which is the European Cooperation for Space Standardization, that has formally specified the quality standards that we need to meet. Internally, we also follow the MISRA coding practices that comes from the automotive industry. And so, the challenge we have is that that level of quality is really demanding, and despite significant investment in our C working environment into, for example, static analyzers and automation of unit tests, code coverage, whatever, we are very reliant on manual code reviews. And this creates a recurring cost time when, whatever the feature, we have to invest a lot to reach that quality. And so the key problem we have right now is that it's very difficult for us to scale our workflow to the modern space challenges required by our customer. So how do we solve that? Obviously, I'm here. So one of the key solutions we are currently studying is Rust. So in 2023, we partnered with the European Space Agency. What we did is that we picked one of our telecom payload software. We selected a subset of the functions, and we re-implemented everything in Rust. And And so the methodology is quite important there because, as you may know, switching programming language is quite a polarizing topic, especially in an industry as conservative as the space industry. So when we organized the study, we focused our efforts into building factual evidence of the potential benefits of Rust. We also, since we have a lot of code reviews, here you have a snapshot of one code review. We get reports from the code reviews, the ongoing code reviews on the C code base, and we try to demonstrate that problem, is it possible in Rust? And finally, since we wanted to achieve results quickly, we had to pick our battles, and we did not rewrite everything in Rust. We focused on a few business-specific functions. And for example, instead of rewriting a complete execution engine in Rust, we chose to use Bevy. So Bevy is a fantastic piece of software. The awesomeness of Bevy does not fit into a 30-minute talk, so sadly, I'm sorry, I won't be talking much about Bevy. I tried, but not possible. Too many cool stuff going on Bevy. Okay, so here you have a concrete example of the kind of challenges we face right now. Previously, we on Boss Software handled maybe up to a few megabytes of data. Nowadays, we are expected to handle up to, let's say, 500 megabytes of data, up to a few gigabytes. And also, the complexity of the features we implement means that we need a lot more processing power than what we had before. And means we cannot use radiation-hardened hardware. Instead, we use, at best, what we call radiation-tolerant hardware. But this hardware will fail in space, on average, maybe once a day. And so we have to mitigate that failure in software. Previously, we relied on the hardware, and now we need to mitigate that in software. So here you have, on the right, you have an example. So here, the application software is running a telecom algorithm that has been mapped in a specific location in RAM. And what we do is that we capture that state. We call it the execution context. And we have another module, which is called the data management system here, that in the background will periodically snapshot that state and save it into reliable storage. So here you have a flash device here. And if we reset, then the goal is to add boot to restore that state into RAM so that the application software can start quicker. So this feature itself is not that complicated. The problem is the space context, and especially the quality constraints. We have a few non-functional requirements to meet. First, obviously, the execution context can be accessed and modified concurrently by the two modules. We need to prevent data corruption. But secondly, the flash device here is not your typical flash device. It's a space-grade flash device that has operating constraints. And the first one is that if we want to maximize the lifetime of the satellite, we need to keep it power on as little as possible. And so today, verifying those kind of requirements in a C code base is up to the quality standards of the space industry is extremely expensive. It's a continuous investment. Every time a new feature is developed in the application software, we need to make sure that the design constraints are still satisfied. And so we rely on extensive testing and peer reviews. So that's an example, concrete example. Let's break it down into 3 pieces. First, let's tackle the data exchange with the flash device. We do not use Ethernet-based networks on satellites. Usually, we use what we call the spacewire networks. It is standards from the CSS. It's both the specification of the hardware forming the network and a family of protocol to be used on that network. You have on the right a description of the few packet types that you can use on the spacewire network. There are 5 packet types that you can use. For the purpose of this talk, we will focus on the RMAP protocols. RMAP stands for Remote memory access protocol. It allows devices on a spaceware network to share state, either storage or to expose their control registers, for example. So you emit commands, read or write, and you receive reply based on the... What is interesting about that protocol is that so there's several packet types. You need to parse the value of the yellow field to compute which packet type you are dealing with. But there's also the structure of the packet, even for a given packet type, is highly dynamic. All the blue fields here are either optional or dynamic in size. So it can be quite complex to parse that reliably and efficiently. So in my department, to meet new requirement about high throughput, low latency data exchanges, we developed a C library, which I think I have on the next slide. There's an example. So here you have an example of the C library. So basically, we expose a frame object that encapsulates an opaque buffer, and then we expose accessors so that you can get the value of the available field in the packet. And we call the set of fields available and the location in the buffer, we call that the frame metadata. So there's a very simple life cycle to use in C. First, use frame init so that you provide the actual storage to store data in the frame. Then if you're reading data, you can use buffer to provide the buffer pointer to some system call so that the data gets actually written in your buffer. And once you have that, you call parse, which will parse the content of the buffer and compute the location of all the fields and all the derived attributes, such as the packet type and the size of, for example, all the blue fields. And if the parsing is successful, then you can use all the getter and setters defined in the library to get the actual fields content. So, for example, if you're reading the content of a first register, the actual content in the read reply is what is in the field that we call cargo, and so you get this kind of API to get the actual value. So first we generated a syscrate, sorry, but we use whitelist to only generate the function we are interested in, to generate the first level of binding, and then we developed another higher level binding in Rust on top of it. And here, when we design the Rust high-level API, we try to solve the typical problem we encountered during the code review on the C library. So for example, here the metadata fields are truly private. And then as you cross in the C library, as you cross the function boundaries or the thread boundaries, it might not be clear the state in which the frame object was. So here we use the builder pattern to make sure that first the storage is actually provided, and then we define the equivalent functions of the C API. But parse is defined on the builder object. If it's successful, then only then you get the actual frame object, and then the getter and setters are defined on the frame object. Okay. So once we have that, we could tackle the interesting issues. For example, as I said, we are now dealing with a lot of data. So for example, a given function can handle hundreds of RMAP frames simultaneously. And frames can be 4 kilobytes each, which quickly adds up. So we had a developer that tried to reuse a single buffer across several frame objects. And you see where it is going. So here, for example, the goal of the developer was to compute the new desired value of a register. So that's why here we have a write command with the desired value of the register. And he wanted to compute the value of that register based on the previous reply he received. And the aim was to copy that data in this one. The problem is since those frames reuse the same buffer, if the developer first set the reply address of the write command frame, then it was actually overwriting the data here. So that's a simple example. There are more complex use cases, and that's actually the nice case, because here you have an immediate problem. You can see it right away that you're actually corrupting the content of a buffer. So obviously in Rust, this is not possible. First, owned and shared buffers are different types in Rust. So it means that in terms of API, we can build different API to correctly handle the differences. And you can see it here. The actual buffer that is used in the builder is an enum, and we model, is the buffer shared or owned? And so this kind of practices helps the library developer. But then in terms of API that we expose to the users, if he's using own vector, then he has all the simplicity attached to owning the buffer. If he's using the shared buffer, then all the APIs here model use borrowing, and so we can rely on the Rust compiler to carefully prevent data corruption. Okay, so we have the first block. We can now efficiently exchange our map frames on the Spacefire network. Now, let's get back to the requirements. We need to manage the flash device. We need to power it on automatically. Let's try to do that together. So what we did is that we first created a type, flash session, to model an active session with the flash. The goal is that in the application, there are as many active flash sessions as necessary. We define the APIs to interact with the flash only on the flash session type. The goal is to restrict the interaction. Okay. Then we need another type we call it the flash endpoint, to create new sessions. Okay. Now, remember, we want to control the life cycle of the flash, which means controlling the life cycle of flash session. So since flash interactions are typically long-lived in an application, they are done in dedicated background threads. So the solution I'm about to show uses cross-beam channels. Okay. So what we did is first, so we define an event, flash session event, that tracks if a session is being created or finished. Then in the new session implementation, we emit the flash session created event. And then we implemented the drop rate on the flash session. When it is dropped, we automatically emit the finished event. And once we have that, the only remaining piece of the puzzle is we need some function that will be called periodically by the onboard software that will process all the received flash session events, and based on the current number of active sessions and the state of the flash device, will trigger a power on or a power off. So if we go back to the first slide when I was talking about the art of multiprocessor programming, for me this is not art. This is simple. This is a simple 5-step recipe. And in the space industry, we're really interested in this kind of stuff. Here we rely, the most unique feature of Rust we rely on is the lifetime analyzers, so that we know that the Rust compiler will automatically insert call to the drop function of the flash session once it detects that object is no longer necessary. And the API exposed to the user is really simple. The actual complexity of managing the flash device is completely done away in the application. And even better, this kind of solution actually scales to the implementation of the other part of the puzzle, which is managing the execution context and preventing data corruption. So here we have a similar design. So the goal for the execution context is to model that sometimes some function needs temporary exclusive access to the execution context. So how we do that? What is the new ingredient that we need to inject in the API? The first one is just the option type. We wrap the execution context in the option type, which expresses in the API that this data might not be available every time, every cycle. And so what we do is that when you create a session that required exclusive access to that field, to that data, we just take the data, which replace that value with none, and we get ownership of the data, and we can, for example, move it in a asynchronous thread. And similarly, when the session is no longer needed, we take the data back, we send it to an event, and then we restore it in the resource here. Okay, so the first new ingredient in the recipe is the option type. The second one is when you're trying to prevent data corruption, you need to track the pointers that are live in the application. And in C, it's really, really difficult because the pointer is just a number that you can copy around everywhere, and we rely on code reviews to track that. In Rust, we have references that are tracked by the compiler, and we know that once a function call completes, unless it has taken ownership of the data, there are no longer any available live references to the data. And so that's the second ingredient we use. And so the key takeaways, we were really impressed by the simplicity of the concept, because we still believe this is simple in terms of API and concept. And those concepts compound with each other and allows us to solve traditionally complex issues in our field. And here, so first, the actual features is really interesting and useful, but all the verification burden that we had to bear ourselves has been transferred to the compiler. And the developer experience is nice and fun. So where am I on term? Okay. So in conclusion, the talk was titled Initial Momentum. Did we achieve significant initial momentum in Rust in my department? The answer is, I think, yes, I was allowed to come. But Rust, as far as I'm concerned, forms a really promising framework for modern on-board software development. So I did not talk about it much, but the development experience, the tools, Cargo and RustNL and so on, are really top-notch. We've also demonstrated as part of this study that we are able to leverage our existing C assets. You don't need to start from scratch. It's usually a bad idea, especially in a field where you have so many quality constraints. But then we were really impressed by the type system, because when Rust claims that it allows everyone to build efficient and robust software, everyone here is really the key. Because the Rust language designers use the ownership, the lifetime analyzer to tackle the memory safety issues. But then everyone can also reuse the same concept to tackle business-specific issues. So for example, managing the power state of the flash or the data corruption issues on the execution context. So everyone can use the same context to inject their business constraints in the type system so that the compiler can check those constraints. And if it compiles, then you have the guarantee that your non-functional requirements are met. So I did a little experiment. You can see on the right here in this diagram. I asked several senior experts in my department to estimate the cost benefits of using Rust in our department based on the result of that study. So the blue line is me. When you drive change, it's important to manage expectations. But my fellow colleagues were really impressed by the results, especially on the verification front. As you can see, they estimate that we can gain as much as we can cut our costs in half, in the best case. So yes, we will continue invest in Rust. I'm still on time. We have identified a few upcoming activities. The first one is, yes, we've estimated that there will be significant gains in using Rust for existing features, but we also believe that Rust unlocks new features for on-board software development, and so we intend to explore that, especially since we are currently working on constellation satellites that have distributed stakes that we are not used to tackle, so that's interesting. The second upcoming continuing activities that we've been monitoring performance from the start. The current figure we have are acceptable, but we need to work on them better because that's a complex topic. We hate micro benchmarks in my field. So we need to be more representative. So we need to implement more features, study the system under heavy load. This requires time, and we also need to understand better what we are doing, especially when using a subset of BV, which we are replacing gradually. In terms of enablers, where we are currently we are exploring partnership in Europe, and we are interested in volunteers to work together with us. So we are using dedicated hardware, which is not currently supported by Rust. We also use specific real-time OS. So in Europe, we use a lot RTEMS, which does not support Rust. So there's ongoing initiatives about that. And the other point is that the ecosystem of Rust is really blossoming. We need to help it mature. And again, we want to support that. And the good news is that there's an ongoing initiative about that, Ferrocin, and we are really interested in that. Thank you. Time.
Excellent. So now it's time for questions. We got 10 minutes. I see a bunch of raised hands there.
Oh, okay.
So you mentioned it's very important in the type of software that you built, the correctness of the code. So I was wondering about tools, formal verification tools that use SAT solvers, for example, to prove the correctness of the code. Is this something that you use? And do you have any thoughts about the state of formal verification in Rust?
So we have, regarding the schedulability of the software, to prove that we meet our deadline, we have, in the case for one core target, we have an actual solver that actually proves the schedulability of our software. For other topics, we currently don't use much. We need first to improve and create our database, our code base in Rust, and then we are interested in this kind of tools. We've looked at Kani, for example, and the other tools. So yes, we are interested in that, but it's maybe a bit early.
Thanks for your talk. You mentioned you did an analysis of an existing code base, existing database of code reviews. I can guess a little bit like what kinds of things you like would be prevented by coding in Rust instead of C, but what are the classes of errors that you found that like you can't, like that are still sort of an issue with Rust? Like what kind of categories broadly would those be?
So what kind of errors can we prevent in Rust? Count?
We cannot prevent by going to Rust. So like what are like the limitations? Like
logical errors, misunderstanding of the specification, errors in the specifications, the typical errors we have during integration, misalignment on between the hardware documentation and the actual capacity of the hardware. This happens a lot. When you're dealing with bespoke hardware, every time.
Thank you for your talk. I was wondering, because I noticed you use drop implementations a lot and RAI a lot. Is there interest in linear types, so types that absolutely may not be forgotten from your industry?
Yes, but linear type, so for me linear type is type that needs to be consumed once.
Yeah, it needs to be consumed, so you're not allowed to forget it or put it in an arc that refers to itself in some way. So like you could have this flash example. You don't want your flash to never turn off again because somehow it's drop implementation that turns it off, got forgotten.
Yeah, it's a tool. Linear type are tools. If they solve, I don't have any specific use case in mind right now, but if it solves an issue we have, we will use them.
Let's see, there's a hand there.
And nice to hear you had mostly a positive experience with Rust. So I was wondering, did you have any noticeable pain points when trying to adapt Rust? One that comes to my mind is, for example, how do you deal with panics in this situation?
So we don't use panics first in our code. Yes, it's forbidden. But regarding your talk, I think I anticipated your question actually. So there's really nice material available about this kind of questions. So I put the links here. So Rust is a complex language, especially so in my case, in my department, people have only known C. So the jump to Rust is actually very, very big. So invest in training. And then do not underestimate for me, the technical side of using Rust was not an issue. Aside from the lack of support from some of our targets. It's more about the human factors, so helping our developers to adopt gradually the language. So you need to start them working in Rust as early as possible, focusing on concrete use cases. Maybe do not start on the key business software first, consider the larger environment, the tools and so on. Yeah, I think that's what I wrote. Yes.
Any other question? I see a raised hand. Well, there's two there.
Hi, I'd like to ask about the radiation. So, of course, you have specialized hardware, but are like random bit flips that could lead to undefined behavior not a concern at all, or not an increased concern?
Sorry, I did not catch the question.
So you have radiation space, right? And
yes.
Those can lead to random bit flips. Of course, you have some hardware shielding. Is the shielding really so good that you don't have to care about, or that the probability of random bit flips is not increased at all, and you don't have to care about it?
We always have to care about it, but the frequency of the failures might drop significantly to the point where we don't need to take specific mitigation actions. But we always, first we need to survive to the reset, because it can be quite violent. So it's always a concern. On satellite, you usually have a specific hardware that monitors the state of all the equipment. We usually call it the reconfiguration unit. It monitors the state of the hardware, or all the equipment. It receives software alarms and so on, and it can generate any kind of resets depending on the issue.
Well, there's another hand there, and more people here.
Thank you. I saw in the examples you were using things like VEC. So that implies you've at least got a memory allocator, or maybe using the standard library. So I just wondered, what platform were you targeting? Can you share a few details about that?
Yes. So for payload, we use ARM-based platform running Linux. So a specific custom distribution of Linux, Yocto-based. Yes.
Okay, thank you.
Thank you. Here, there's a couple of questions more. So we'll go for the last question. I just got a signal from here.
You mentioned the maturity of the ecosystem and referenced ferrocene, so presumably the formal spec of the compiler. Is there anything else in the maturity of the ecosystem that is immature?
There's a lot of crates to choose from, and what we need is a curated list of crates that have support, that are maintained, documented. So this needs funding. We need to work on all that. But yeah, that's the kind of stuff we are interested in. I think those ideas are already around.
All right. So just before Alex comes up and tells us what's going to happen next, I have this little present for you.
Thank you.
Thanks for speaking with us today. Thank you. Enjoy it.
Thank you.
So, are we live? Yes, hi.
You should show them your new.
Yeah,
thingy.
no, don't even get me started, because this is the most important thing. You can now get various glitter tattoos. That is what we're doing in the break. So in Chaos and Chemistry, Chaos and Chemie, next door, we're now going to go for a break where you can have a drink and catch up with your friends and get glitter tattoos. I got mine in black because all of my tattoos are in black, but they're in every color you can imagine, so it's going to be great. Can't wait. Everybody show them after, okay? Anything else I wanted to say? No. Please make sure that you check out the sponsor stands. They're all set up now. Everybody's put in a lot of hard work. And they're also the people who make today possible, so check it out. The weather, gorgeous, absolutely beautiful. So that's going to be great. For this break and lunch, we expect you all back here at 11:50. So you got half an hour, a little bit more. And then after the break, we're going to have Alice Reel to talk about Arch and the Linux kernel. Thank you so much. See you later.
Excellent.
Could be worse. Derek is in charge of. Hi. Do you need we need you 10 minutes for get the mic on. That's all. Hey, nice. saying something. Yeah, you're all so well behaved. I asked for 10 to 12, and here we are. Everybody's back, and you all went quiet. That's amazing. So who got a glitter tattoo? Like 4 people, really? And they asked me to stand more in the light. See, because otherwise I'm just a silhouette standing in the back. Okay, before we get started, I got a couple of household messages. So I think about 8 people asked me where the toilets are. So next to the entrance, at the front of the building, there's this orange container. That's where the toilets are. Also, across from there, in the lab, that is where the workshops are. And they will start at 2 o'clock. And last but not least, there's also a quiet room there. So if you're completely overstimulated from everything that's been going on, and you just need a place where you can just chill out for a little bit, there's a quiet room next to the lab. So across the entrance, just keep walking straight. And for the workshops, 2 o'clock. Was that everything that I had on my note? Yeah, so the live stream is sponsored by Hyperswitch. Thanks a lot. I also understand that, I think I said at the beginning of the day that it was going to be streamed directly to Vimeo, but it's just on YouTube. I thought it was a copyright thing. And let's see, I want to thank FutureY again for making this possible. Because they're the headline sponsor, and none of this would be possible without their help. And with that, I would like to introduce the next speaker. Hang on. Huh. Yes. So my next cue card said drinks. And I was like, what? Whoa, that was quick. What happened? Yeah, no, it's Alice Real. You are from Denmark. Absolutely. I asked. Because I was like, that's a Swedish name, right? No, she's from Denmark. She's also a core maintainer of Tokyo and part of the Android Rust team working on a driver for Linux in Rust. But today, you're going to be talking about Arc in a Linux kernel.
Yeah.
Thank you. Take it away.
Hey everyone. Oh, I have slides. Awesome. Yeah, that's the first slide. Okay, thank you for coming. I want to talk about the Linux kernel today, Rust in the Linux kernel, and Arc. So, yeah, it's something I've been working a lot on recently. A bit of context. So the Linux kernel, you know, it's a kind of a special place. For a long time, they had this rule that you had to use the C programming language to develop code there. But it's no longer the case, right? Now you can use Rust. I have some info up here. Yeah, you know, it started in 2020. Then they sent an IFC in 2021. In 2022, they actually said, yeah, let's try it as an experiment. So Rust is in the kernel as an experiment right now. And so in my case, I'm working on one of the Rust drivers. It's called the binder driver. It's used for Android for sending messages between processes. But that's not really what my talk is about. Because, you know, Rust in the Linux kernel, what does it take? So real Rust drivers used in the Linux kernel, that's really, really important. Right? If nobody uses it, they're just going to rip it out. But that was my previous talks. So that's not what we're talking about today. Today, I want to talk about, you know, the Rust language and what happens when you put the Rust language into, let's say, a new environment, which the Linux kernel certainly is. You know, there various things, good first impressions, Back when we started, you had to use unsafe blocks every time you created a struct because, working with the C types and so on. So we don't do that anymore. That's a pretty bad impression if you have to use unsafe all over your code. Now, what I'm really talking about today is Arc, but specifically unstable compiler features related to, I'm going to deep dive into Arc, but it's a general thing. And it's actually, it's a problem for us that we are actually requiring a specific version of the Rust compiler because we have to support, the unstable features, right? And they change when you upgrade the compiler, unlike stable Rust. Now, it's not actually as bad today as it has always been. We used to have our own, forked version of the alloc crate of the standard library, and the standard library uses a lot of unstable stuff internally. We're getting rid of that fork, so hopefully the amount of churn related to specific versions will go down a bit. But we still need a bunch of unstable features, so it's a problem. And to understand why is this actually a problem, we're Rust developers. We know how to, we just do Rust up and that's it, right? But once you're a distro that wants to ship Linux and they want to use Rust in their Linux build, right? They're not going to use Rust up in their distro builds. They're going to use their own Rust compiler. What are the chances that the Rust compiler they ship match what the Linux kernel needs? Well, if we supported a fair number of versions, the chances would be pretty good. But today, the chances are very low. And even if they match today, in a few months, they're not going to match. And there are, this problem goes on and on. There are also cases like when somebody who does C code submits a patch to the kernel, we would like them to, compile their code locally with Rust enabled before they send their patch. Maybe they changed the header file that broke some Rust code. But they're not going to bother if they have to go look. If they can't just use the one from their distro, a lot of them are not going to bother. This is just some of the problems. Anyways, enough about that. What am I talking about today? Essentially, I'm going to talk about why is the Linux kernel special, right? Why is it that we don't just do the same thing as you do in normal Rust? Why don't we just use the standard library Arc? Well, today I want to talk about what makes the Linux kernel different. And then at the end, I'll mention some specific unstable features that hopefully are on their path to being stabilized. Now, I promised to talk about Arc. Arc stands for Atomic Reference Count. The idea is you have some shared value. And so you can have many Arc handles that reference the same shared value. So normally the shared value is immutable, but you can make it mutable. And one of the benefits of having it shared is that not only do you use memory many times every time you clone it, but also if you modify it, all of the clones will see it. And so the way Arc works is that when you have an Arc, you can call clone, and then you get another Arc. But it doesn't actually do a deep clone. It doesn't clone all of the data. That's the idea. And so then they get destroyed, the counter goes down. When the counter goes 0, the destructor runs and cleans up the memory. That's all an Arc is. Now, the standard library for Rust has a type called Arc that works like the one I just showed you, but it's special. You can't implement your own. Or at least you can't implement your own fully featured version. So yeah. One reason is, so this counter, what happens when it goes all the way up to the maximum number? Well, it wraps around to 0, and now you have a lot of handles, but the object got destroyed because you had a 0 in the counter. So what Rust does is that when this happens, it just calls abort, so it kills the program. So in the Linux kernel, they also have reference counting. It's not a Rust-specific solution. But in the Linux kernel, they have a different way to handle it. And we would like to use the Linux kernel's solution, like the solution that the Linux kernel has agreed to use for reference counting. That's what Rust should be using too. And for example, when it hits the maximum number, we replace it with some special infinite value, and then it just stays there forever. And this way, it never wraps around down to 0. Now, so when this happens, the value can never go back to 0, so the memory never gets cleaned up. But that's better than calling abort, right? What happens if you call abort in the kernel? Well, your machine just turned off. So this is also a bit of a technical issue. So there's this whole issue with the memory model. The Linux kernel came up with their own memory model for how to use atomics. And we're supposed, we discussed for a long time, should we do what Rust usually does for atomics? Or should we mirror what C does? And what C does involves some inline assembly, and it's kind of, let's say, specific to your architecture, but it works for them. And we came to the conclusion that we really should use the same atomics as the rest of the kernel. There are many good reasons for this, but the point is, the arc is not doing that. And so that's another reason. They're also nice to haves. When you work with C types, a lot of these C types build in some sort of assumption that their address doesn't change because, well, they're stored in some linked lists or whatever. But the point is, they require this thing called pinning, which a lot of you have probably heard of, and a lot of you probably don't know the details of. But the point is, we need pinning all of the time. And so we made our arc include pinning by default. Now, you could do this with the standard library, but just wrapping every arc and pin. But it's nice to have that we can do it in our own way. Another nice to have is weak pointers. So a weak pointer is when you have a reference that doesn't prevent the value from getting cleaned up. We don't really need this, and in implementing it involves several counters. Yeah, removing it simplifies our arc, so we don't have it. Yeah. Now, these unstable features that you actually need to implement your own fully featured arc, we also have some other types that we want to use them for. So stabilizing these features would also let us use them for them. Let me tell you about the first unstable feature. It's called arbitrary self-types. So if you've used Rust at all, you've probably seen &self and &mute self. But you can also write functions like this: self:\arc self. And this basically means that instead of an immutable reference or a mutable reference, you get an atomic reference counted reference when you call the method. This is very nice because when you have the arc, you can call self.clone inside the function. So this is a nice thing. Now, this particular example I showed you, we could work around this. It's not a be-end and end-all thing, right? But it's still a nice to have. But as you will see later, there are some other cases where we actually do need the feature, and it's not just a nice to have. Now, to an entirely different topic, linked lists. So linked lists are hard to implement in Rust. They're famous for that. There's a whole book called Learn Rust with Way Too Many Linked Lists. And you know, sometimes when people want to learn Rust, they say, oh, linked lists are simple, right? I'll start with implementing a linked list, and then they'll have a bad time. But anyways, you know, and you don't even want linked lists most of the time because they have worse performance than vectors. But the kernel still needs them. And the problem is, we have something very special that you don't have to deal with in user space called atomic context, which it's basically a short amount of time where your thread is taking up the entire CPU core. Like nobody else can run here, so you can't context switch, that is, replace the thread with another thread during this critical region. Okay? And one of the consequences of this is that you cannot allocate memory, at least not with the standard ways, because allocating memory might call into stuff that will do a context switch. Now, imagine that you have a vector here. Now, so one example of this atomic context is what's called a spin lock. And a spin lock is kind of like a mutex, if you're familiar with that, except it's super fast. But while you have the spin lock, you're in an atomic context. And so let's say inside the spin lock you have a list. And I want to push a value to the list. Well, how do you actually implement insert on your list if you're not allowed to allocate memory? So if you're using a vector, the problem is the vector has some amount of free space, and there might not be enough. And if you run out of space, you have to allocate memory, but you can't. So what you have to do is return an error, and then you can leave the spin lock, make a vector with enough space. Then you can re-enter the spin lock, copy all of the data over, and put it in. You could do that. But, well, this gets kind of cumbersome, right? Because now if you did anything inside the critical region before you tried to call push, then if you get an error, you have to undo it. It's not so nice. But with a linked list, that's no problem. Right? Because with a linked list, here's a linked list. You have these next pointers and previous pointers that point to the different items. I have a new item down here I want to insert. So I just, change the pointers. No allocations is needed for that. Like this object is already in an arc somewhere. So it's already allocated a long time ago. So that's easy. Yeah, so it looks like this is the idea. We have linked lists in the kernel. And so this is a super simplified example of what it actually does, but the idea is you have 2 pointers. They're actually wrapped in like a struct, but they have 2 pointers. And then we put this thing in an arc, and then to insert, we just update the pointers, and that's it. Very nice. But there's a problem. The problem is you can have many arcs to the same value. I mean, that's the entire idea. That's why you're using an arc, so you can have many references. But what if you have 2 clones to the same shared value? Well, you only have 1 pair of next previous pointers inside the value. So what happens if you insert the 2 clones into 2 different lists at the same time in parallel? I'm not going to go into the details, but the point is you're going to have a bad time. You're going to have a data race, then which list does it end up in? Maybe both? I don't know. Your lists are corrupted now. Don't do that. So the solution we came up with is a new smart pointer, like the arc called the list arc. So you can have many arcs, as usual, but at most one of them can be a list arc. And so the idea is that the previous next pointers they're kind of owned by the list arc. Right? And Rust's ownership model works very well for this because the list arc is like an object. You can transfer ownership. And so you always have a single object that has ownership over the previous and next pointers. And so if you want to insert this into a linked list, you just pass the list arc to the linked list. And then nobody else is using the pointers right now, so we can insert it. Why do we have these linked lists? So at least why I use them, is this queue of events. So we get, we have a bunch of events. We put them in a queue. The linked list ensures we have an ordering. And we're using a linked list because the vector runs into this problem with atomic context and allocations. Okay? Now, when you have a queue of events, you probably have many event types. So it's really a linked list didn't event trait. And so this gets into the other unstable feature. Because now we want to use didn't trait with arc. Right, so it looks like this, right? We saw this before. So we have a trait called event trait. And it has, a run function or whatever. And then we have self::list arc. We saw this before. That's this unstable feature called arbitrary self-types that lets you put the, arc, or in this case the list arc, as the argument. Now, of course, the list arc, it's important to, move around ownership, right? Like, you only have one. So if you don't pass it into this function, well, the function now doesn't have the ability to use what the things that list arcs give you permission to. So because of that, we can't just use &self. Yeah, so the point is, when you have, so the way it works is you have a list arc of your event struct. It's some struct containing the event. And then you want to convert that into a list arc didn't event trait. But that conversion, it works with the standard library arc, but adding that conversion to your own types is unstable. So here's one unstable trait. So all of this, at least the way it works right now in the compiler, is that we have an unstable trait, coerce unsized. So coerce is this conversion operation, and turning a struct into a didn't trait is an unsize. So that's why it works. It's called like this. And we want to implement this trait, and it's all nice. We also need another trait. This is so when you call the trait function, right? You already have a list arc didn't event trait. Right, but when you then call it, then inside the function, it's actually going to be it's going to look up what's the underlying event type, and then it's going to go into the code where you know what the event is. So now you actually just did a conversion from list arc didn't trait to list arc event type. And that's what this trait does. So dispatch refers to looking up the function with the right event type. And you might not have noticed, but there's another trait here called unsize, and that's also unstable. Okay, well, so we came up with a solution. We discussed this a lot between the Rust for Linux people and the language team. And the solution that was proposed is the thing called derived smart pointer. Because the problem is, we have these 3 different traits. And we don't even know, we know that the way they look right now, that's not what they should look like when they're stabilized. Right? But that makes it kind of difficult to stabilize them. Because then you have to sit down and think really hard about designing programming language and figuring out what do you do about that? What's a better design? And then you have to implement that. So, that's been tried before. There's a pre-RFC up there about attempting to do that. But our proposal is, we need this today. Can we stabilize, like, can we take this large feature with these many traits that we don't even know how to look, can we reduce the scope, right? When you don't know how to do the thing you want to do, reduce the scope. And so what we're going to say is, we add this macro, you put it on your struct, your list arc struct and your arc struct, and that's it. This macro generates these traits behind the hood, but the macro is shipped with the compiler, so it can be special. But we don't stabilize what the macro expands to. And this is, kind of unusual, but it's not totally unheard of, because, we have a test macro for tests, and that actually expands to some unstable stuff related to the, benchmarking suite and testing suite. So they can change it in the future. And so this idea is simply, make it so that we can start using the feature now, and we can continue working on the underlying traits. Like, don't lock us in on one specific answer. So, just before RustNL, I posted this RFC, proposing to add this derive macro. So I'm hoping that will be stabilized soon. And that's it. Go take a look. Yeah, this is the end. In case it was unclear.
Let's see. Okay. Any questions? Here's a question.
1, 2. Thank you for your talk. My name is Vlad, and I'm with Rust for more than 10 years. I think I started to learn Rust even before 1.0 stable release. And at that time, I already was surprised that in Rust there are a lot of magic around standard smart pointers, for example, box. And for example, you can move a value out of the box. And there was a lot of RFCs to fix them. For example, implement the ref move for box pointer, but they were left without any moves, or even were rejected because there wasn't any practical value. So what do you think? Is it good time to get rid of all the magic around all the pointers, including box? Is it beneficial for the language in general? What do you think? Thank you.
I mean, I do mention in my RFC that reducing the magic of the standard library is nice. And so, box is an example of something that's even more magical than arc, right? Arc is a bit magical, but box is really magical. Like, you can move the value out, which is like the only thing place where you can do that. It's kind of like, we don't really need it, right? We're working hard on stabilizing the things that we actually have a real reason, like, that we need a lot, right? And this is something we need a lot. I think it would be cool to see movement on, and maybe this, making progress on this smart pointer issue can help others to, move on other smart pointer issues. I do also, this issue doesn't really cover smart pointers containing custom allocators. That's also a future possibility.
Then we have an online question. Someone is asking that at the start of the talk, you said that the implementation of arc aborts whenever the reference counter reaches I size max. Why is it an I size and not a U size?
Okay, hold on. Okay, so the basic idea is like isize max is basically, halfway around the integers, right? So you have up to isize max, and then you have just as many numbers above that. And so the reason for using isize max as the, let's say, threshold where you do like special stuff is that, for one, like if you hit this number, it's still a bug, right? On the other hand, if you use usize max, right, then let's say that 3 threads run in parallel, hit increment at the same time. Well, some of them are going to see, oh, the ref count is 1, right? Because it wraps around, and the other thread is going to call abort soon, but it hasn't done so yet. And so using isize max means that now you have to call increment in parallel from, what? Billions of threads in parallel for any of them to see it actually wrap around, right? So it kind of gives you some time to call abort before the other threads see it actually wrap around.
Any more questions?
On one of the slides, I saw a struct with an intriguing name called unique arc. And since arc is all about putting more than one thing in there, I was wondering what that's about.
Good question. I can't find, well, whatever. So the idea is, let's say you make an arc, right? Or like, here we go. So let's say you want to create an arc inside an atomic context, right? You can't allocate memory there, but creating an arc requires that. So what you do is that first you create a unique arc containing, uninitialized memory, and then in here you initialize the memory and then you convert it to a normal arc. Does it make sense? Right, because that way you allocate the memory beforehand. Yeah, and so it's kind of like this idea that it's unique for some time. It's also how you create the list arcs, right? You take a unique arc, and then you convert that to a list arc, because now you know that there's no other list arc out there, right? Because the unique arc is unique.
There's a hand there.
So from this talk, it appears that there's a lot of effort involved in getting Rust into the kernel, so thanks for that. I was wondering about the process of getting this accepted and also getting some foundations for, there's a lot of contributors, so do you still experience that there are tribes of like the old C camp and then now there's the Rust camp, or do you think it's right now a joint effort across the kernel to get it in there?
There's a reason I try to say the Linux kernel needs rather than the Rust for Linux needs, right? But, there are the people who come, into the Linux kernel from Rust. And then there are people who, have worked with C for their entire lives and now need to learn Rust, right? It's a different experience. And yeah, it's a real difference, that you're not just, it's not just gonna go away magically. And it's also why, right? Good first impressions for people coming from C.
Yep.
Right?
Yep.
It's there for a reason.
Yep. Thanks.
There's a hand there in the back. This is the last question.
Yeah, thanks for your talk. I think you use a lot of unstable features probably. What is actually your most favorite unstable feature which you hope will get stabilized? Thanks.
The thing I want to see most stabilized?
Yeah, or what you find. Either what you want to get stabilized the most, or what you find most joyful to use. Whatever you want.
Well, I put a lot of effort into working on this IFC and pushing this particular feature forward. So that's certainly the one I have let's say, invested the most in. We also have some features where sometimes people say, maybe we should use this feature to do this cool thing. Then I say, let's not do that. Let's not use min specialization, right? Let's not make that one of our blockers, if we can help it at all, right? Because some features are harder to stabilize than others.
Excellent. So I guess this is the moment to thank you again for the talk. And
thank you.
So next up is Mara Bos. You probably heard her name or seen it in places because she wrote this book, Rust Atomics and Logs. Not those of the Linux kernel, but there are other ones. And she's also a library team lead. She founded a company called Fusion Engineering. She lives in Delft. There will be no QA after this talk, but you can think about whatever she says and come talk during lunch. So please come up and take it over.
Hi, my name is Mara. I'm a member of the Rust project, and today I'm going to talk to you about the evolution of the Rust language. Specifically, I want to zoom into how a feature gets added to the language, to the standard library, or its tooling. And this process starts with you, the user. You are working in Rust, and you have any kind of problem. A stumbling block could be a big thing, something that's currently impossible in Rust, or it could be something small, some functionality you're missing in a standard library. Then you spend time thinking about that problem. You come up with an idea, and eventually you write down your solution, you work it out, and eventually you can submit your solution as a proposal to the Rust project in the form of an RFC or an ACP. And if everything goes well, then in the end, the relevant Rust team will look at it and hopefully approves your proposal, after which implementation and stabilization happens. But that's not the focus on this talk. I want to start with a show of hands. How many of you are Rust users? How many of you have written any line of Rust code? Good. How many of you had any kind of problem in Rust? Anything where you thought, like, oh, if only the language would work slightly different? I see a lot of hands down. Apparently, you all think the Rust language is perfect. That's great. I'd also want to talk to you afterwards. How many of you spend more than 5 minutes thinking about your problem? How many of you had an idea on how to solve your problem? Maybe you knew which method you wanted in the standard library, or you had an idea of which language feature would make your life easier. How many of you actually wrote it down in a blog post or RFC or anything like that? Okay. How many of you submitted an RFC to the Rust project? And how many of you and how many of you got their proposal accepted? So at every step, there's fewer than before, and that makes sense in a pipeline like this. But I want to zoom into how these things break down. And there's a few obvious ones, of course. Maybe you don't have time to think about your problem, or maybe you don't have enough context to come to a solution. Maybe you don't have time to write it down, or maybe your proposal gets rejected. But let's zoom into one particular frustrating sequence of events that happens in reality a lot. It starts with a user in the Rust project, and this user has a problem. And in this case, it's a complicated problem, something where there's multiple possible solutions. It will interact with other problems. So this user wants to come talk to us, the Rust project, because we have all the context, except we just don't have a process for this. The process for changing Rust is by submitting a solution to us, and then we'll judge the solution. But talking about problems, that's not something we have a fixed process for. So you follow this process instead, where you think about your problem, and you come up with the idea, you write it down, and you submit your solution to the project. And then we say no. Because maybe your problem is a really important problem that we need to fix, but maybe your solution is actually not the right one. And this is a very frustrating moment, because this no doesn't mean that your solution isn't important, or your problem isn't important, but it does send you all the way back to step one. And then if you have more energy, you can do this thing all over again, take some of the feedback from last time, come up with a new idea, write it down, submit a new RFC. But there's still no guarantee that it will be accepted, and it might just be rejected again, sending you back to step one, at which point you might just do something else that's more fun. This slide represents frustration that quite a lot of people have experienced. And the problem is this dotted line. Everything on the right side of this dotted line happens inside the Rust project. But everything on this side happens outside of it. You might be able to talk about it with project members, but it happens maybe on blog posts, but maybe on a whiteboard at your office, maybe just in your head, all over the place, but it is not coordinated by the Rust project. So every time you come with a solution and it gets rejected, you get thrown over this wall, and you're on your own again. So I want to talk about tracked and untracked work. So looking at this picture, just like I mentioned, this part is what we track in the Rust project. If you submit an RFC, it will become a pull request on the RFC's repository, and you can see the discussion going on there. You can see whether it has been approved or not, the outstanding questions. You can see after it's been approved, how all the steps towards stabilization. You can see how the implementation is going, etc. So we keep track of that, or at least we try our best. But all of this stuff is untracked. We don't have an overview of all problems that you all have. Most of them we never even hear about because, well, with the show of hands, I saw that lots of people had problems that they just don't end up writing down because the only thing we accept as written down things are solutions, not the problems. So all of this stuff stays untracked and invisible to us. So let's take a look at what we could track. Or at least what we could track if we had unlimited time and energy. We don't. The reason we don't track all that stuff is not because we hate you or we hate problems, just we don't have time. But imagine for a second we had infinite time and energy. Then, well, the most obvious thing we could start tracking is actually the problems themselves. Instead of just having an overview of all the solutions that have been tried and which ones have been accepted or not, we could start tracking which problems people have, which problems we're trying to solve. We could start tracking negative results, because something that happens to me a lot, and probably to others too, is that I think I have some brilliant idea, I work on it for weeks or months, and then in the end I realize, oh, it doesn't work. Just throw everything away. And that feels like a failure, like a waste of my time. But it becomes a failure if I don't write it down, because then a few years down the road, someone with the same problem will do all that work all over again. But if we actually started tracking negative results, if I had a place to post my result, like, hey, I tried this, this doesn't work, then someone else could take that on and continue where I left off. The same for partial results. Maybe you don't have a full solution, but you do have some key ideas towards the solution. And perhaps most interestingly, user research. You might have a lot of interesting information about how users use Rust. Maybe you represent a user group in, for example, embedded or game dev. Or you might have a lot of information about how Rust gets used at your company. Or you might spend a lot of time on GitHub code search and know all kinds of patterns that appear in real-world Rust code that point at a specific problem. So today, if you do any of that research, you don't have a way to submit that research to the project, only if you take that research and turn it into a proposal, a solution, and then you can come with that to the Rust project. But we're not very good at tracking any of this, and that's a shame. So doing all this stuff is a lot of work. I'm not sure if we could. But if we imagine if we did track problems. Imagine that we had some sort of map where each of these blobs represents a problem. And it could be high-level problems, like performance and binary size, or it could be a specific use cases we care a lot about, like Rust for Linux or embedded. And we could track all kind of low-level, more specific problems, like mutex poisoning or efficient string formatting. For each of these problems, we could keep track of negative results, partial results, ideas, and most importantly, how they relate to each other, which ones depend on each other, and any other kind of connections between these problems. If we had this map, then if we would, for example, prioritize binary size, if that's something we wanted to do, just an example, then we can look at this map and see which things relate to that. Just follow the lines down this graph and see which other things we should prioritize. While some of these things might be obvious, there will also be things there that are completely unobvious because they are several steps away. And this is exactly what Nico has been working on. Shout out to Nico over there. Nico has been working on something called project goals, setting up a process for setting goals as a project as a whole, so we can actually, we can actually try to prioritize something not just per team or per person, but as a project as a whole, because many efforts, like for example binary size, require efforts from many different teams. Check out the RFC. I think earlier today, or maybe yesterday, there was a blog post on the Inside Rust blog. I didn't have time to put it on the slide, but go check it out. But if we had this map, then it would be a lot easier to see how all these things relate when you set a goal, which other goals you shouldn't forget about. Very similarly, this is very useful for funding. Imagine that the Rust Foundation gets a grant from some big company. Here's 2 million euros, and go spend it on binary size and Rust for Linux, because they tend to get funding for these high-level problems, not for the low-level ones. Then you can start to follow these arrows down and see what the money should be spent on. Because today, if you're working on refactoring Bootstrap and you try to get money for that, you'll just get a no. No one cares about that. People care about that. And only with this map you can tell them, well, actually, if you want that, you need that. And finally, if you are a contributor who's working on a specific issue, for example, you're just hyper-focusing on extern types because it's just so cool to work on, then your world might look like this. You just focus on that particular thing. This happens a lot. But with this map, you can zoom out, and you can see how your problem connects to other problems. You can find connections between problems, find connections between solutions, and most importantly, find connections between people. Because every single one of these blobs represents not just a technical issue, but they represent people. People with that issue, people that want to work on that issue, people with ideas, people you need to collaborate with, people you should talk to. So, back to the main point of my talk. The entire point of this talk is, let's talk a bit more about the problems, instead of only focusing on the solutions. Let's focus more on this part of the process, because this part, we've been undervaluing it. We might need a bit of a culture shift where we start valuing problems and thoughts and ideas more, even when they don't necessarily lead to a solution directly. So the question is how? How do we do this? Do we start tracking every thought in the world about Rust? I don't think we can do that. There's a few things we can do, like Nico's project goals is a great step towards this, but I don't have a full solution. I don't have the answer. So it might be a bit of an anticlimactic ending to my talk. I don't have an answer. I don't have a grand conclusion. But the entire point of the talk is that we should be able to talk about problems, even when we don't have a full solution. But I do know something, and that is that we should be making more connections. So I have 2 assignments for all of you. 1, during lunch, which will start right after my talk, Go talk to each other. Talk to someone you've never talked to before, and tell them about a Rust problem, your Rust problem, and listen about their Rust problem. And try to find a connection, any kind of connection. Because this picture today, with this many people around, looks like this. Many users, many problems, many thoughts, many ideas. And if we all start talking to each other about them, this picture turns to this. We can start combining our thoughts, finding patterns in problems. We can come up with bigger ideas. The second assignment I have is to come talk to us. Nico and I have set up a booth in, it's all the way in the other building at the far end. And you can come to us with your problems and bring us your Rust problems. We'll write them down and try to make them part of a bigger picture. And hopefully that will end up with something useful and exciting. So, talk to each other, come talk to us. Thank you for listening, and enjoy your lunch.
Thank you, Mara. I thought it was a really, really inspiring talk. It was straight, very close to sort of what I try to do at the Nelnet Labs instead of all of the programming talks that I don't really get to do. Anyway, I am in between lunch and outside and sunshine. So I'll try to make this quick. We have an hour and 50 minutes for lunch. And then I expect you all back here at 2. Lunch will be served across the street again in Dutch, chaos en chemie, so chaos in chemistry. But I invite you all to go sit outside. It really is a gorgeous day. You've got sunglasses prepared and everything. And after lunch, we'll have Joe Burr-Crixton to talk about Isham Russells. Also, the industry track will start at 2, and registration inside Chaos will start for that at 1:30. So if you want to be part of the industry track, make sure you go and sign up there. And the afternoon workshop will also start at 2, where you get to design user interfaces using MakePad together with Rick Arends. So that should be fun as well. And then I'll stop talking because I'm going to let you go, and I will see you back here at 2 o'clock. Enjoy lunch, everybody. Thank you.
just trying to see if people will come in quicker if I stand here. All right, let's go on. So I guess we have less people now because the workshops are ongoing. And again, we wanted to take the opportunity to thank the workshop partners, one variable, MakePath and Main Matter, and also to thank the Rust Foundation, which is an ecosystem partner of this conference, for making this possible. And now I'm going to introduce the next speaker. But before that, I want to tell a story. I'll keep it short. So I originally sent a proposal for a talk for this conference, and it got rejected. It was about the Russells, because I worked on that last year for ISRG. And I was like, well, I got rejected. That's pretty bad. But then I discovered that we have the Russells OG with us, the original author of the library. So Joe Pixton, please, he's here with us. And he's the original author and maintainer of Russells. He is currently funded by ISRG, the makers of Let's Encrypt, to work on Russells. And he's going to tell us how they're going to replace OpenSSL.
All right, thank you very much for the generous introduction. So, I'll roll back a little bit on that. I'm not completely replacing OpenSSL, but you'll see the details in a minute. So this talk, I'm going to give a little brief at the start about what we've been doing in the Russells project over the past year. And then I'm going to be talking mostly about this new sort of side project called Russells libSSL. Why we're doing that, what it is, and then some technical details about how we're achieving it. So yeah, first thing is funding. So as Adolfo mentioned, I started Russells in 2016, so that's 8 years ago now. And for the past year, I've been like one of those few people who are fully funded open source maintainers. Scary, but really great. And so there's me, and there's also Daniel McCarney, who's another full-time, fully funded maintainer of Russells. And then we've got our third maintainer, Dirkian, who's involved with this conference and has spoken here in past years about Russells. And as Adolfo mentioned, we've had some project work as well by him and Ferris to do, various focused changes to Russells. So yeah, very good. Very happy with how this has turned out over the past 8 years. I don't know how that quite happened, but great, why not? So we've been using all this huge amount of time that we have to catch up with features that people have been asking for quite a long time. Especially things like no stutter support, which Ferris did a lot of work on, obviously, given their background. The other thing that I think is quite interesting and feeds into a lot of future work is this pluggable cryptography providers work. So we basically sliced off the bottom of Russells. So that top part of Russells doesn't depend on any particular cryptography library anymore and is pure Rust. And then we take dependencies through create features on Ring and AWS LCRS. So you can, if you want, have a completely pure Rust TLS library, but you do have to bring make a choice of where the cryptography is coming from. There'll be more work on that in the future, I think, from not just us. So, yeah. Now I look a bit stupid rolling back on replacing OpenSSL, but we're going to do it bit by bit. And this is the first bit, I think. A small sliver of the first bit. Let's not get ahead of ourselves. The reason we're doing this is I think we've done quite a good job of implementing TLS in Rust for Rust people. But slightly less of a good job about taking that good work and making it usable for people who aren't rewriting everything in Rust. And so this is an effort to do better at that. The other thing to say is there is like a big problem in computing generally with memory safety. And if we can sort out that in small parts rather than huge parts, so what I mean by huge parts is throw everything away, all your software away and rewrite everything in Rust, or throw all your hardware away, and ARM and Intel would like you to do this, and get things like memory tagging and an ever-increasing number of new CPU silicon features. Replace all your hardware, throw it in the landfill, buy new computers. I don't think that either of those are very tenable, although in this room, I know what most people would choose. So yeah, I want to give a big shout out to this. I love this graph. This brings me joy. So this is the UUtils project, rewriting GNU core utils in Rust. And not only that, running the GNU test suite for core utils against their code. So the nice part of this graph is the green up and to the right. That's beautiful. So unfortunately, to understand this talk, you have to know a little bit about how OpenSSL works, and I really apologize for putting this in your brain if it's not already there. But important things is OpenSSL builds two libraries, libSSL, libcrypto. Invariably, if your application uses TLS, uses OpenSSL for TLS, you end up linking to both of these. There's no way around it. You end up with both. But you can, if you don't use TLS, you can just use libcrypto for other things like, well, whatever you want. In almost all cases, OpenSSL is dynamically linked against your program. That is generally for replaceability aspects. So if there's a vulnerability in libSSL, you just replace this. You don't need to come and relink or recompile your application. So this is a little bit different to how most Rust applications are deployed, but that is how it's done. That's the world in which we have to work. And so that brings us to a missing emoji, which is meant to be scissors, but whatever. Basically, we can chop this out, right? So what do we need to do? Well, we need to implement this interface, which is the libSSL API, or ABI, if you want to be really specific. And we need to implement this interface because one of the things in libcrypto is like error reporting. So when something goes wrong in OpenSSL, there's an error reporting API in libcrypto, and you basically say, this went wrong, here's the line number information. It's like, you know, build your own backtrace sort of thing. And an application will then go to libcrypto and say, I just got told there was an error, please tell me about the error. And if that information is missing, then you haven't done a very good job of replacing libSSL. This is the next problem. libSSL is huge. One wow, I can actually read that. I didn't expect to be able to read this, but I imagine no one else can. So 522 functions. It's actually worse than that because this is OpenSSL 3.0, and now it's 585 in the latest one. So it's growing, and it will continue to grow basically forever, I think. Oh, God. But there's more, right? Because that's not all the functions that people might call. And again, I'm going to apologize for showing you some C preprocessor. If you don't know C preprocessor, this is a function which looks like a function but isn't. It gets replaced by the C preprocessor to this expression, which calls a different function with a bunch of fixed and variable arguments. And there's 136 of those. So there's like hundreds and hundreds and hundreds of things that we need to write. But fortunately, that is a long tail of unused, weird stuff. And if you have some focus and say, we want to target curl, we want to target Nginx, which is exactly what we've done, then you end up with this short list of, this is doable. This is some functions, we can write functions, great. Nginx, if you choose both, 114, that's a couple of months' work. As it happens, we've implemented 132 right now, but that doesn't seem very interesting. The main thing that you should take away from this is not a complete replacement for libSSL. You cannot take any arbitrary libSSL using program, slide this underneath it and have it work. But what we're doing is basically incrementally qualifying individual things. So at the moment we've got curl and Nginx on a particular version of Ubuntu. Later I'll do another release of this, which will add Ubuntu 24 for Nginx. So that's how we're attacking the problem, not trying to attack the entirety of that problem by writing 700 odd functions all at once. So this is the rewrite it in Rust part of the talk. And so what do we need to do? We need to write a new dynamic library, and we can do that. We can just put that in our cargo toml, and it works. Oh, that was easy. The next thing's not so easy. We need symbol versioning. So this is quite annoying. OpenSSL uses symbol versioning, so when you load a dynamic library, you usually look up things by name. Symbol versioning adds a new dimension to that, a version. And the intended idea is that you can evolve your ABI over time by just having different versions. But we need to do that because the dynamic linker complains if your application thinks it wants this version and it gets a different version. And this is annoying because the standard way is you give a linker version script to the linker, which we can do. And this typo here, LDD, that should be LLD, that the LLVM linker, that's what we have to use. The annoying thing is RustC uses the linker version script for itself and doesn't re-expose that, so you can't tell it what version a symbol should be. You basically have to do it after the fact. Using LLD fixes that because it's happy to accept two, more than one, linker version scripts. So that all works. And how it works is, in our Rust, we define a symbol like underscore SSL connect. In our linker version script, we define SSL connect with that version. And then we also tell the linker that these two symbols are the same. And yeah, that works. That was a little bit of hard one. knowledge from various people. It's not original stuff. And that is what this build.rs is doing. So the next thing, well, we can write some functions. And we want to write hundreds of these functions. So macros to the rescue. And I'm not going to show you the innards of these macros. I think that would be cruel and unusual. But suffice to say, we have a function. We have a file with hundreds of these in, and it basically decorates this function, which looks like a Rust function, but actually it's no mangle and extern C. The other thing that is important is if a panic happens in our Rust code here, we have to make sure that doesn't bubble up into the C code, because that is undefined behavior and everything will go really badly wrong in a confusing and uncontrolled way. So it also wraps the whole of this function body in catch, unwind, and then does a bunch of things. It tells the error handling mechanism that I was talking about earlier that this has happened, and then it returns a null pointer in this case. So we just have an error type that knows how to be converted into a bunch of C return types. Yeah. So now I want to talk about testing. This isn't new work. This is a thing that has a Wikipedia page and everything. But I like it. It's nice. It's cheap. It is cheap. Did I say cheap? Really cheap. So basically, you write a whole load of C programs, and you call the function that you're interested in. In this case, 2 functions at the same time, because they do the same thing, really. And these functions take an int, and they're only usable when an int is between 0 and 255. So we obviously check from -1 to 260. Why not? And it just prints all the output. What is this getting towards, Joe? Well, that's what the output looks like, and then we run it against the real OpenSSL and our thing. And you can probably see where this is going now. They should be identical. And you don't need to do this with very simple functions like that. The most important thing is that the output is deterministic. So you really must, you cannot print the time, you cannot print any encrypted data. And that is a bit annoying. Also, you can't have non-deterministic data structures determining the output. But one thing to say is that OpenSSL has quite a lot of callback-based APIs. Making sure that those callbacks are called at the right time with respect to other functions is pretty important, because that's what people expect. Well, that's what their programs expect. And this basically linearizes the program flow with respect to what functions are called and what functions were called by OpenSSL, as long as you just print out when everything happens. So yeah, that's good. The other thing to talk about is MIRI. So obviously, when you're writing unsafe Rust, you probably use MIRI. And if you don't know what MIRI is, it's like an interpreter for the Rust compiler's internal representation, or one of the internal representations. But it cannot work if you make an FFI call. And that is because in an FFI call, there is no Rust internal representation of all the binary code in libcrypto. It doesn't exist, it won't ever exist, it cannot exist. And so it gives you this error. This is a great error. I love this. typical of Rust errors, right? What's gone wrong, where it's gone wrong, what to do about it. Oh, beautiful. But at this point, I'm thinking, I am absolutely perfectly capable and willing to write a dodgy version of X509 store new. Please let me do that, Miri. Please let me do that. And I'm like, yes, I'm going to send Miri people a pull request adding this. It will be great. This is such a great idea. And so I go and find where this error comes from. And I find the code leading up to that, which is like symbol resolution. You've got this X509 store new, and you want to know what to do with it. And I find the code's already there, and it actually already works. So all you do is you write your slightly dodgy X509 store new. So to be clear, this isn't the code we ship. This is just support infrastructure to run a different test. And what this different test needs is to be able to get a unique non-null pointer from X509 store new, and then later on pass it to free and have that work and not produce any Miri warnings by itself. So yeah, I just wanted to say that because I didn't find that and I had to go look in the code, but I was pleasantly surprised. So what have we done? We've made a memory safe, mostly, replacement for OpenSSL 3, libSSL, so that's like half-ish of the project. Mostly is doing a bit of heavy lifting. Obviously, it's a C API, so if you call a function with that takes a pointer with the pointer 1, 2, 3, 4, 5, it's not going to work well. You cannot possibly fix that. You can't have memory safety from that level, but everything below that, everything that is reading network traffic and stuff, is memory safe. And, well, obviously, yeah, you don't need to recompile applications. You can just try it. You'll see on the next slide, and see how it works for you. And yeah, it's a small subset of the libSSL API at the moment, but I think it will grow over time and support more applications. And yeah, it's quite easy to try. So we have a package that you can install on Ubuntu or Debian right now. Probably more packaging to come. It comes with a couple of handy scripts, like with Russell's SSL, which just runs a sub-process and fiddles with the linker settings as it does that. So that's how you can run curl. And another little helper which fiddles around with Nginx's systemd configuration to make it use this rather than the main system thing. So when you install that package, it doesn't overwrite the OpenSSL one. You have to kind of opt in on an application-by-application basis to say, use this by fiddling with linker parameters. Right, that is it.
Hello. Thank you so much. And now it's time for questions. Who has a question? Ah, there. And somebody, there is a mic right there.
Hi,
Excellent.
thanks for the talk. The focus of your talk seemed to be mostly on the FFI. Were you actually rewriting all the functionality that's in libSSL, or were you using existing crates from the Rust ecosystem?
So a lot of it is just kind of converting between OpenSSL's view of the world and Russell's. So, you know, OpenSSL's got its own idea about what a cipher suite might be, so we have a type which represents that. But inside, that basically refers to a Russell's type. It's not a perfect match. So if you know the Russell's API, there's this config object. I think our documentation says, like, try not to make a lot of these. We make, in this project, we make one per connection because the configuration is quite late in the OpenSSL API. You can, like, basically call things in any order you like. And then when you finally connect, that's when it's set in stone. But there's nothing like that in the Russell's API. So we are using some other ecosystem traits. Crates, I've got Russell in the mind. Like OpenSSL Probe, which tells you where the standard locations that OpenSSL looks for certificates and stuff. But yeah, mostly it's a semi-direct glue between Russell's world and OpenSSL world.
Nice. Oh, more questions? The person next to you, right there. Thank you.
I had a question to you. How does your library work together with libcrypto?
That is a very good question. So at the moment, it's not ideal. So we're not using libcrypto for crypto. Instead, we're shipping a libSSL which contains a different libcrypto. We plan in the future to have as a separate crate a Russell's crypto provider which calls down into a libcrypto and then wrap those both up so that you get a more like obvious, well, not obvious, a less surprising thing, so you don't end up with your libSSL holding loads of crypto. Also, that would be quite useful to other users, I think. Say, if you want to make use of OpenSSL's FIP certificate, then you'll be able to use that to do that.
All right. Have we got time for lots more questions? There we go.
Did you find memory leaks bugs in OpenSSL itself while re-implementing it?
Now you put me on the spot. Yes, but I'm in process with OpenSSL about that, so I can't really talk about it. Yeah. Which is a shame, because it would be nice to come and say, oh, we replaced loads of stuff with memory safety, and by the way, while we were doing it, all the wheels came off, but the time didn't work out. So.
All right. More questions over here? Yes, all the way in the back over there. Running. No, hang on. Otherwise, we won't be able to record it.
Does Debian have plans to make RustTLS the default provider?
I can't talk for Debian, I'm afraid. But, I mean, I know they package it, and that's one step along the way. I would hope they might package this as well. And then maybe you could have, like, I forget what depackage selections or whatever it's called, where the system maintains a bunch of symlinks and you can choose as a user which libSSL you want.
Update alternatives.
That would be quite nice.
Thank you.
All right. Anyone? Yes, over here in the front. Oh no, wait, hang on. Wait, if you go there, then it's logistically easier. I'll get to you. I'm not going to forget you.
Yeah, the entry macro, is it something that's generalizable between like different crates, or is it something specific that's to OpenSSL?
I would say it's quite specific, basically because of the error type. It makes errors, and those errors know how to be inserted into the OpenSSL error stack. Yeah, that seems quite obvious. But on the other hand, it's like 5 lines of macro, maybe 10, because I think it has to deal with functions without a return type. It makes it really annoying. But yeah, please steal it if you find it useful.
Thank you.
All right. And then there was a question here in the front. I'm sorry, I'm making you run all over the place. There we go.
Can this
be a basis for having RustTLS be itself dynamically linked for programs using RustTLS? Or are there lessons you've learned for doing?
So we actually have another project called Russell's FFI, and that is a better C API to Russell's. And, well, confusingly, there is, in curl, for example, you can choose to build with Russell's as its TLS under thing, and that uses Russell's FFI, because obviously curl's all written in C. And that is a C API as well, so you can dynamically link that if you want to do that.
All right. Anyone else? No, over there. Excellent.
So, excuse me, are there any performance implications for this sort of translation between, you know, the C API and particularly, I suppose, the API that OpenSSL expects and kind of Russell's internal stuff?
That's a good question. We haven't actually measured performance in a meaningful way yet. I don't think there should be a big difference. At the minute, Russell's and OpenSSL are roughly on par in terms of performance. There will, at some point, be a little bit of a performance degradation because we're going to start using some more of the APIs in libcrypto for stuff like maintaining the list of trusted certificates and stuff. At the moment, we don't use any of that, which is a bit of a defect because you can just go and add a load of certificates to an object that our library is completely ignoring. So that will involve a little bit of conversion overhead for every certificate validation. That may or may not be visible in performance benchmarks. I guess we will see.
All right. Anyone else? Yeah. There's a question here. Actually, I also have a question myself, but I don't want to block anyone in the audience, so otherwise I'll just ask you later.
So you mentioned the goal is kind of to replace OpenSSL for applications like Nginx and curl. Is there kind of a path forward to, in practice, in Linux distros, replace OpenSSL with this crate for those applications, or is the idea to kind of finish the implementation first and then replace it wholesale?
Ooh.
So kind of my question kind of is, what's the path forward for replacing OpenSSL in practice?
Yeah. I think probably, well, there's a lot of old things in OpenSSL. I think if there is, like I mentioned, there's this long tail of their API. What I'm not sure about is whether there's a long tail of people who rely on those things. If there is, that's going to be more difficult for absolutely getting rid of OpenSSL for good. But you can kind of imagine a situation where, already someone's shipped a product that I know about, which is a Linux distribution which uses curl built against Russell's. For those more kind of limited applications where you control a lot more and you don't have users wanting to install this old bit of software, then it's much more durable. So having it as an option in those sort of circumstances is a good start. I think then building up more applications that support this is probably the direction we're going to go with, rather than aiming for completeness.
Thank you.
Right. So, if I may, the question I had was, did you actively aspire to be like a fully funded open source maintainer? And when that came across your path, like, was it like a hard choice? Like, I'm giving up something stable, and who knows how long this will actually... How did that come about, and is it something you would advise everyone to sort of aspire to if they have the chance?
Yeah, I would like to say if there was some sort of trick, but there really wasn't. It was very accidental and lucky, I think. And yeah, the offer was on the table there for a little while I was still working at a big tech company. But yeah, eventually it just became too desirable to like just go and do my own thing. But to be honest, I was doing anyway, mostly in my spare time. So like, why wouldn't you? Yeah.
Thank you so much. Thanks again. We have a gift for you, Adolfo. That's really excellent. Thank you. So our next speaker is Leon Scheuermann. Did I pronounce your name correctly?
Pretty good.
Oh, God. PhD candidate in computer science at Princeton even. He maintains a TOC operating system written in Rust, designed to run mutually distrustful applications.
That's
I can't
correct,
believe
yeah.
it. But that is not what this talk is about, right? It's about fortifying Rust FFIs with encapsulated functions.
That is correct, yeah. Thanks so much.
I read it from my cue card because this one I could try to memorize it. Terrible.
Yeah. No worries, yeah.
Hey, take it away.
Yeah, so as was introduced, I'm just going to wait for the slide to pop up. Oh, that does not work. All right, let me see whether I can reconnect this. Sorry about that. Maybe that should work. All right, there we go. Yeah, so thanks so much for the introduction. I appreciate it. Yeah, so I'm a PhD student at Princeton, and I want to talk today about my latest research project, which is exploring sort of safe interactions between different programming languages in a project called Encapsulated Functions. As I said, I am also a maintainer of the TOC operating system, and while this is related, and we're going to show how exactly this relates, it is a different project. This is work I've done together with my collaborators, Jacques, Tyler, May, and Amit. Yeah, and without further ado, let's get right through it. So I want to start my talk with a statement which I think should not be controversial in this audience, which is that I think that memory type-safe languages are generally safer, more reliable, and more secure. They increase developer efficiency and encourage fearless development, and they prevent entire classes of bugs due to their construction. So for instance, you're going to be unlikely to be seeing use after free type confusion or other kinds of bugs in Rust. And we see that these advantages are recognized throughout industry and other circles. So for instance, Microsoft is rewriting some core Windows kernel code in Rust. Linux is obviously experimenting with Rust, as we've seen. And Google is writing some core components of their Android operating system in Rust. What we can also see is that based on their reporting, they also see a significant drop in memory safety vulnerabilities and an associated drop in the severity of these vulnerabilities, which kind of confirms that these suspicions even work, these advantages even work in more constrained environments. But this raises a question, given that sort of in the conventional wisdom, these type memory safe languages have dynamically enforced type memory safety, which introduces significant overheads. They typically tend to be garbage collected and thus introduce unpredictable timing behavior and memory allocations, and can have quite high overhead foreign function interfaces and interactions with native code. Why do we now see this language be popping up? And we attribute this to a new class of sort of safe systems programming languages that is emerging, of which, of course, Rust is one of those languages that feature a combination of compile time, type, and memory safety. For instance, reference or region-based memory management as opposed to garbage collection for more predictable memory management, and direct ABI compatibility to other languages. And they also commonly can interface with low-level assembly code directly, which allows us, for instance, in the TOC operating system to implement context switches or trap handlers in inline assembly in Rust. So a reasonable question to ask at this point is, why does my operating system still have access violations and can crash because of those? And in essence, this is kind of what we're trying to solve. But I guess a less provocative way of stating that is that parts of our systems will continue to be written in these unsafe languages, not just for the foreseeable future, but we think that's something that's effectively set in stone. This is has a multitude of reasons, but partially this is because operating systems in particular are built on legacy software. They might be written for machines that are no longer commercially available, and those machines, or the code for those machines, might make assumptions about particular language semantics that are different between different languages. And in general, we're just getting started rewriting our code in Rust, so I guess it's just going to take a bit of time until we get there. We also have external constraints that in certain environments entirely prevent the use of safe languages. So for instance, in an embedded system, if you want to use some cryptography component, chances are that you're going to have to use some, or going to have to go through some industrial or governmental certification processes. And those processes sometimes indirectly or directly prevent the use of certain languages. And finally, software also provides us reusable libraries. So as we've just seen, for instance, OpenSSL is one of those libraries that's pretty universal. And while we do now have an alternative that we can use, which is very nice, chances are that you're still going to be using at least some of these libraries, even if they're written in a safe language, perhaps not the exact language that you want to use for your project. And this kind of establishes the basic premise of this work, which is that we identify there will not be a single systems programming language, and the software must continue to interact with code written in other, perhaps unsafe languages, and we need a mechanism to safely interact between different languages. And what we're proposing is in exactly such a mechanism, which is encapsulated functions. It's a system to facilitate safe interactions with component written in foreign languages by considering the aspects of both memory safety and type safety. Before we can go into exactly how encapsulated functions work, we first of all have to understand a bit about the particular issues we're addressing and the background. So here I've depicted a simple system that consists of memory-safe application written in Rust that perhaps makes use of some cryptography implemented in C. So this could be OpenSSL, some networking library in C++, or even some math functions in Fortran. One way to realize these applications today is to use operating system process isolation, which is a very nice mechanism that gives us strong isolation guarantees between those languages, but it's also typically associated with pretty high overheads. So this means that when you want to communicate some data between your memory-safe application and your foreign library, you're going to have to incur some serialization and deserialization cost, perhaps copy some data. And even if you use efficient implementations of all of these processes, there's still going to be a context switch involved between every such interaction, which can be a pretty high cost compared to some pretty short-lived functions. Instead, what you can use is the safe language's foreign function interface, which allows it to emulate the ABI of a given other language. So in Rust's example, this could be the C ABI, and as such allows Rust to directly call functions that are written in, for instance, C. This is nice because the entire program runs in a single address space, which allows the foreign code to exchange data efficiently with the safe application. And a function call is literally the cost of a single jump. This is how something like this can look in Rust. I'm pretty sure the previous talk has shown some similar examples, and you've probably already seen something like this. We can define an extern C function symbol in Rust that just announces to the Rust compiler that there is going to be a given symbol that it is linked to, which implements a given ABI. In this particular example, I'm using this AS encrypt function that I've invented. The particular semantics and parameters are not super important here. Just do note that it returns a Boolean value. And then in line 11, we define a Rust wrapper around this function. And this Rust wrapper then invokes this function on line 13 and stores the result in a variable, and finally moves this variable into an enum, which is defined on line 6. So pub enum message is an enum which has an encrypted and unencrypted variant. Notably, because this is a tagged union, both of these variants are going to be stored in the same memory location and are thus overlapping. Given this example, one of the most apparent ways in which this can break Rust's memory safety, as we've heard in the last talk, is when, for instance, the foreign code is not well behaved. So Rust may have some allocations that it assumes exclusive ownership over, and so when foreign code is either handed a reference which it shouldn't write to, for instance, it's a shared reference in Rust, or just invents some other arbitrary pointer, it may endanger Rust safety in a variety of ways simply by writing to its memory. And so memory safety bugs in these libraries compromise the overall system safety. There is, however, also another type of issue, which is a bit harder to spot. even if we assume that these libraries are entirely well behaved and our interface code with them is sort of superficially correct, the different cross-language semantics between these languages can introduce additional hazards. And to explain this issue, we're going to have to go into a bit more details of the previous example, particularly this pub/enum message type. So we can see here again that this enum type has two variants, which I've outlined here on the slide, and I'm depicting their memory layout. So we can see that the first word of memory is occupied by an enum discriminant, which just indicates what the active variant of that enum is right now. And then all of these subsequent data fields are just laid out in memory effectively, according to their alignment right after this discriminant value. So we can see here that the message encrypted variant has a discriminant of 0, and the message unencrypted variant has a discriminant of 1. This is, however, a rather inefficient representation, and Rust recognizes this. In particular, bool is defined sort of semantically equivalent in Rust to this enum that I've depicted here. In particular, it's sort of a 1-bit value that can either assume the variant false or the variant true. And it is, however, stored in a memory location that occupies at least a full byte full byte's worth of memory. And so what this means is that we have a couple of other uninhabited values that we could be storing in this memory location where the bool is stored. And so Rust performs an optimization that is known as niche filling, where it actually combines those first two fields, the discriminant and the Boolean value, and treats both the values 0 and 1, so all valid values for a type of Boolean, in this first field, and then uses the first uninhabited value of that type to denote any other discriminants that we might wanna encode. And so ultimately this saves us a whole lot of memory, and that's a nice optimization. This can break, however, when, for instance, Rust then reads a value of type Boolean, that it assumes of type Boolean, that has been modified, for instance, by some foreign code. This is because foreign code does not necessarily need to adhere to the constraints that Rust places on its types. And so if, for instance, Rust were to read a numeric value of 2 in this Boolean field, then we could be storing this message encrypted variant here, and storing a vec besides the Boolean, as is illustrated in the enum's definition. But we could be reading back, because we're storing this value 2 in here, and Rust assumes that the Boolean type is valid, and so it doesn't perform any other checks, the unencrypted variant. In this particular case, we would be able to safely dereference what we believe to be a C string type, but is actually a vec pointer, and that ultimately leads to undefined behavior and, in practice, segmentation fault. And so Encapsulated Functions is a project that tries to address both of these issues through a set of interworking mechanisms. We introduce a mechanism called safe trampolining that allows us to isolate the memory between safe and untrusted foreign code. This mechanism is platform agnostic and retains sort of general function call semantics. Function calls remain to be synchronous, and so it's more or less a drop-in solution for existing bindings. And then we combine this with a type infrastructure that is responsible for securing these cross-language interactions in these more tricky cases where we have sort of mismatches in the definitions of types across languages. And this is enforced entirely at compile time, so you should be unable to write any code that violates these constraints. And if it doesn't, or when it does incur runtime overheads, those should be minimal. We'll be focusing on the safe trampolining aspect first. It's worth mentioning at this point that Encapsulated Functions does rely on the presence of some memory protection mechanism in the system. So we're agnostic over the exact mechanism used. This could be a hardware-mediated memory protection mechanism provided by the operating system, for instance, regular address space isolation, as is implemented in the memory management units of the computers we use today, or more primitive mechanisms such as memory protection units, and more modern mechanisms like x86 memory protection keys, which is a mechanism that we're using to evaluate encapsulated functions on. We could also be compatible with something like software fault isolation that does not rely on the presence of hardware mechanisms. However, we do not explore that at this point. And so this is depicting a regular sort of Rust application, in this particular case running in the context of a microcontroller system. So we have a memory map that contains a couple segments, in this case some RAM, some flash, and some memory mapped I/O. And when we now load a library into this system, we load it into a set of coarse-grained allocations that is disjoint from any Rust allocations. And so here we're loading a library with its RAM contents and flash contents placed in the appropriate memory allocations. And we might even give it access to some hardware peripherals. This could be useful, for instance, for a cryptography accelerator. We then set up a memory protection mechanism to allow our foreign code only access to these particular allocations. It must be unable to access any Rust allocations, or at least write to those allocations. The converse is not true for our Rust code, however. Because we assume Rust to be well-behaved and a type of memory-safe language, it is going to be limited to dereferencing its particular sort of currently valid allocations. And as such, we can and indeed must allow Rust to access, or to be able to access this foreign memory. When we implement this in practice, there's kind of three key challenges that we need to solve. We need to load foreign libraries into a disjoint set of allocations first. We then need to set up memory protection, set up the memory protection mechanism to enforce sort of the protection policy that I've illustrated on the previous slide. And then finally, we need to switch protection domains. And these are arguably the most interesting of those challenges, and so we're going to be focusing on that. So the problem is basically that we must restrict untrusted foreign code to its own memory allocations. And the intuition behind this is quite simple. We can just enable memory protection, execute the foreign function, and disable it again. However, when we do this naively in practice, there's a couple of challenges that we need to solve. For instance, we cannot simply enable memory protection in the host language itself, in our case in Rust, because we don't have fine-grained control over the sort of end result, the binary that the Rust compiler produces. Between any two statements, Rust is free to insert arbitrary memory reads and writes to allocations that it deems valid. And so once we enable memory protection and are still in the Rust context and want to call another function, this may actually break our host program ourselves because we could get access fault violations. For obvious reasons, we also can't rely on the foreign code to enable this protection mechanism because it's untrusted by definition. Instead, we need to switch exactly on the function call itself, and that's rather tricky. We also need to maintain access to function parameters and return values when we execute foreign functions. Depending on your architecture and depending on the precise callee, so the function signature that you're calling, some arguments might be passed in registers, whereas other arguments are passed on the stack. And if we simply call a function from within Rust, Rust is then going to spill those arguments on its own stack, and that is going to be located in a memory region that is inaccessible to our foreign code. And we solve these challenges through a callee-specific safe trampoline that I'm going to be illustrating next. So this trampoline works as follows. For any given C function definition, in this case, I'm taking one which is called random bytes buff, that takes a pointer and an integer and returns another integer. We then, using Rust bindgen, first of all, generate a Rust function signature that implements this function's ABI and calling convention. So we denote it here as extern C to instruct the Rust compiler to, when this function is called, prepare an execution environment that is effectively appropriate for calling this function. It has all the right arguments loaded into registers and spilled on the stack. But obviously, we don't want to just invoke this foreign function in this execution context, because then we would be invoking it with Rust's privilege set. Instead, we're going to be aliasing this function to a custom invoke symbol that we're introducing here, which is implementing our trampoline mechanism to, in sort of one atomic step, enable memory protection and switch to foreign code. So this is written in assembly typically, and its basic job is effectively to just copy all the stacked arguments, enable memory protection, invoke the foreign function, and then when it returns, which works through a springboard mechanism that is dependent on the precise memory protection mechanism that you're using, we then disable memory protection and copy the return values back, in addition to any sort of required status flags. So for instance, if the foreign code were to have an access fault violation, we would want to return to Rust and actually indicate that there has been an error. However, this is still not quite sufficient because we might be loading multiple instances of this library into our program. And so this invoke trampoline can't really know which library instance it's currently talking about. It needs to know, for instance, where the foreign memory is located, where the current stack pointer is to copy those arguments. And as such, we're adding an argument, we're appending an argument to this function signature, which we call context. Here we rely on the fact that when you append an argument to a function signature in all of the calling conventions that we're aware of, this does not change the location of any preceding argument. So this is effectively still a compatible execution environment. Another problem is that now we have this context struct, and we can resolve a couple of things about our library, but we don't know exactly where this argument is going to be passed in the function. And so instead of just providing one such invoke function, we make this into a generic function that is generic over the amount of bytes spilled on the stack by that particular function signature and the location where this context argument is being called or is being passed. And so in this particular example, the context argument is passed in the second argument register of, I think this was a RISC-V based calling convention, or the RISC-V-C calling convention. And now, and we do this, we generate these arguments by extending Rust bindgen with a static analysis pass to analyze our function signature and sort of have a small implementation of the particular calling convention for that architecture. But that's quite brittle, so in the future we would actually like to query the LLVM backend. That's still to be implemented. And then finally, because this function is now a different function signature and you need to pass this additional context argument, and also we need to do some other work such as interpreting whether the function actually had a fault violation and returning an error result instead, we provide a wrapper function signature that then simply calls this function. So with this mechanism, we now can transition from Rust code into C code, which is quite nice. But this is not really particularly useful in isolation because of the problem that we talked about where Rust technically is able to access foreign memory based on the memory protection policy, but it can't do so because it's limited to only accessing its valid allocations. Rust does provide the unsafe escape hatch for us, which is nice. It allows us to upgrade arbitrary pointers to references, but as the name implies, that's also really dangerous if you were to violate any single one of Rust's guarantees that it requires you to maintain. And so what we instead propose is another component, which is the type infrastructure that is responsible for securing these cross-language interactions. We base this type signature on simply a raw pointer type. We treat this as an arbitrary pointer into foreign memory, but really it can point anywhere. It can point to a dangling value, misaligned value, value of an improper type. And because it's not safely dereferenceable, retaining this value and passing it between safe and foreign and safe Rust code is going to be sound. Then from this value, we can perform an operation which we call upgrading. Upgrading takes this value and checks a couple properties, namely whether it's well-aligned and a mutably accessible object, and whether it's entirely contained within those foreign memory allocations, which ensures that it's disjoint from any Rust allocations. And then using this EF_mut_ref type that we're creating here, we can support a safe write operation, which is unable to violate any of Rust's semantic guarantees. Then finally, from this type onward, we can also run a function called validate that then actually checks whether the pointee of this reference happens to be an object that conforms to Rust's requirements on valid values. For instance, whether a Boolean is only going to contain a value of 0 or 1, not 2. There are some objects for which we can check this at runtime, namely Boolean, char, or string. There's other objects or other types like references for which we simply cannot check this, and thus this operation must be impossible. And then there's yet another couple others like integer types, which are simply universally valid. They don't have any particular constraints imposed on them. We can also represent this on sort of a timeline where we take this raw pointer and then we upgrade it into this EF_mut_ref, which continues to exist for entire program execution, and then validate it into this EF_val, which also continues to exist. However, while that's safe in isolation, it can actually be quite dangerous when we pair it with some other operations that encapsulated functions exposes. For instance, let's assume that you have a pointer to a Boolean and you upgrade it and you validate it, and so we're all good. We can dereference it into a proper Boolean type. But now we invoke foreign code, and because it has access to all of its memory, it can simply retain the original pointer to this value and write an invalid value, according to Rust's definition, to that memory location. And so invoke is kind of a dangerous operation where beyond the point of invoke, we cannot rely on these guarantees to be valid any longer. Quite a similar issue exists for the mutable references, where if we free the memory that belongs to the underlying allocation, accessing this in the best case is just going to result in an access violation, and in the worst case, Rust may actually reuse this memory for some proper Rust allocations. And now our EF_mut_ref type has successfully produced mutable aliasing, which is unsound and we thus must prevent. We fix both of these issues by introducing two new types, which we call access and allocation scopes. Those function quite similar to capabilities or Margo types, if you're familiar. The important invariant that we need to maintain on those types is those are singleton types. There must only ever be one instance of each of those per foreign library that we load. And when we now have such a type, we can extend these operations that we have here to make use, to sort of use them to bridge Rust's concepts of borrowing and lifetimes onto foreign memory that is otherwise not conforming to those requirements. And we start by taking this validate function and having it take a shared reference to this access scope. Thus, it sort of adopts this access lifetime here. And while that's in isolation is not particularly useful, we can take any number of references, any number of shared references to a type. When we pair this with a modification of the invoke function, namely having this take a unique reference of this capability, the Rust compiler will then ensure that beyond the point of invoking this function, no validated references that borrow the previously active shared lifetime or sort of shared reference lifetime of the access scope will be in scope anymore. And thus no validated references sort of can still be dereferenced across this point of invoking a function. We do quite similar modification using allocation scopes to the upgrade operation and free. Namely, we take a shared reference to our allocation scope in the upgrade operation, which binds the mutable reference and transitively also the validated reference to an allocation scope. And then we take a unique reference in a call to free, which then ensures that beyond that call to free, these validated reference or these upgraded references must have gone out of scope. In practice, our implementation does something a tiny bit more complex, namely, not every single reference is dangerous to keep around in the presence of any given single free operation. There are free operations which simply do not deallocate any memory belonging to particular references. And sometimes we can actually steadily determine this in our code. And by extending the mutable reference type with an additional lifetime, we can, for a subset of these references, prevent them from going out of scope across certain free functions or free invocations. And so with this system in place, we can now safely dereference values in our foreign memory from within Rust, subject to a couple of other restrictions, such as the foreign library not being multi-threaded. What remains to be seen is actually the sort of what overheads this mechanism imposes. And for this, we perform some evaluations using our implementation, which is a research prototype. So it's not quite ready for prime time yet. In particular, the code quality still needs to be worked on a bit. We have two implementations, namely one for the Linux userland using an Intel MPK or x86 MPK mechanism. Memory protection keys is a quite attractive mechanism for encapsulated functions because it is a hardware-based memory protection that you can control entirely from within user space, and thus you don't incur a context switch across the protection domain switch between different language components. We also have an implementation for the TOC operating system kernel on the OpenTitan Silicon Root of Trust, which is a RISC-V chip running at 24 megahertz using the physical memory protection mechanism of RISC-V. And we extend Rust bindgen to generate these encapsulated functions bindings from C header files. We evaluate sort of three representative workloads, which are libsodium as a popular high-level encryption library, broadly as a compression library that's used by Google and Dropbox, and cryptolib, which is a hardware-accelerated and hardened cryptography library for the OpenTitan Silicon Root of Trust. And what our evaluation shows is that in most cases, the overheads that encapsulated functions imposes are quite negligible. So we compare ourselves against an unsafe baseline that neither performs any memory protection nor performs any validation operations. So the validation operations here indicate that we only use our type infrastructure and impose that on the code. The invoke-only benchmark only uses the memory protection but does not perform any validations. And then encapsulated functions is sort of those two combined. It should be noted that in the first two benchmarks, we do actually perform some validation in practice. So the fact that these overheads are quite minimal is just an artifact of the Rust optimizations on these benchmarks and them being quite lightweight. So here we perform the validation that the strings returned after these functions are actually valid UTF-8, which Rust requires us to maintain. For the hash function, we also invoke our validation routines. But because the hash functions output an array of integers, of bytes, and those are universally valid, the Rust compiler is actually able to optimize these calls away entirely. We have a slightly more pronounced overhead on our second target, which is the OpenTitan FPGA implementation running at 24 megahertz. So obviously these numbers are quite a bit larger on an absolute scale. Relatively speaking, we're imposing sort of a 50 millisecond overhead compared to the unsafe baseline. And this can be explained by two factors. First of all, the PMP, physical memory protection, requires us to do quite a bit more operations to actually perform a perfection switch. Effectively, we're performing a context switch in this case. And the other reason is that because we're running an HMAC workload, we do actually need to copy quite a bit of data into the unsafe foreign code domain for the HMAC to be able to operate on that data. And so about roughly like 80% of the overhead imposed here is actually spent on copying data versus switching the protection domains. And so to summarize, encapsulated function secures interactions with foreign languages through its combination of both a safe trampolining mechanism to isolate the memory of foreign and Rust code, and by securing these cross-language interactions with our set of type abstractions. The preliminary results that we've seen are pretty promising, and we would like to extend our work by improving the calling convention analysis that we're doing. Right now it's a bit brittle, so if we use the compiler backend, hopefully that should be much more stable. We want to do a thorough safety and soundness analysis of our code, because obviously we internally use quite a bit of unsafe Rust, and so we would need to be careful that we're not actually violating any of Rust guarantees. We're pretty confident in the overall sort of setting of this. And in particular, for Linux user space, we have experienced that some libraries, such as we have a benchmark which is using OpenGL, that doesn't quite work with this because they rely on global symbols and shared state too much. And so if we were to sort of rework the dynamic loading and the way that we use the dynamic loader in our implementation, we might be able to support even more targets seamlessly. And with that, I would like to thank you very much, and I'm happy to take any questions.
Excellent. Well, who dares? There are two hands there.
How would this work for dynamic linking?
That's a good question. So we are, in fact, only supporting dynamic loading right now. So the way that we achieve this separation of different sort of disjoint, isolated, coarse-grained regions is we use a function called DLM open provided to us by glibc that loads, where we can effectively load libraries into their own namespace. And so I think, does that answer your question? That effectively means that we can sort of dynamically load libraries.
Yeah, it does. Thank you.
Thanks, that was interesting and a lot to take in. I have something that I didn't quite understand, which is when I pass a data structure to C, for instance, do I actually copy it or can I pass a reference? And if I'm copying everything, isn't that expensive? And do your benchmarks show that? And then a related question is, I didn't understand the multi-threading story.
Yeah, that's a good point. So there's sort of two models of this solution. Technically, it doesn't violate Rust safety, or Rust soundness at least, if you can read Rust memory from within a foreign language. And so depending on your particular thread model, you might enable read access to all of Rust memory, in which case you can skip copying in the majority of cases. In our evaluations that we do, we did copy data So all of these are copying admittedly rather small payloads, so on the order of a couple of kilobytes, because these functions themselves already were quite long-running compared to the overhead of copying. And if we had copied more data, that would have made those functions take longer and would have effectively eliminated even this tiny bump that we're seeing in the overheads here. So copying does incur overheads if you do enable read and write isolation of memory. So that is quite expensive compared to, of course, not copying. For the second question, that was about the multi-threading story. So the reason why we don't support multi-threading right now is that our type infrastructure kind of relies on the temporal invariance that we're maintaining here with respect to these capabilities. If our foreign code were to be able to execute while we are assuming to have unique ownership of this value, and while we're assuming that it doesn't change, then we can no longer rely on these guarantees. So we're still kind of figuring out the multi-threading story here. What you can do is you can use multiple instances of a library across different threads, and you can have your Rust part be multi-threaded, just the foreign function needs to be single-threaded.
There's another hand.
Great talk, thanks.
Thanks.
I was wondering, does this system support like callbacks? Like some applications expect a function, like I think OpenSSL is one, for instance.
So we have a proof of concept implementation of this, and it seems to work quite well. It fits actually quite naturally. It's certainly less polished than all the other consistent components we have. So before I commit to us supporting callbacks, that's like the small asterisk. But there's nothing really preventing this from happening. The one thing that you need to be careful about is what we've also seen in the previous talk, is that you need to catch unwinds and panics in a callback when you call Rust. When you call, I guess, C from Rust. Wait, Rust from C from Rust. Yeah.
Got it. Thanks.
There's some hands at this side.
Does this work with multiple libraries, like recursively?
So you would say that effectively this is loading a library in the library that we're then interacting with?
Yeah, so if you have a C library that uses a C++ library, which you then call from Rust.
So as long as the C library dynamically links to that other library, or statically for that matter, this should work because we're then loading both of those into the same linked namespace and isolating both of them. In fact, all of these benchmarks that we have for Linux user space do use something like glibc, which works. But if those libraries were to then use dlopen and sort of dynamically load other libraries at runtime, that is currently unsupported. That's kind of an implementation detail in our current version.
All right, thank you.
Hi. Newer Cortex-M microcontroller chips usually come with TrustZone nowadays, which has some overlap with what you're saying or what you're talking about here. I was wondering what your opinions are, because it doesn't look like you're using it. Maybe there's good reasons.
So I will admit that I have limited understanding of TrustZone M. That's the microcontroller variant of TrustZone. As far as I'm aware, it's effectively an additional layer of memory isolation that has some stronger guarantees with respect to control flow. In that case, I don't think there would be anything preventing us from using this. In fact, we do have a prototype which uses the ARM Cortex-M MPU. So that's the memory protection mechanism that is effectively the equivalent of a RISC-V physical memory protection on ARM. We aren't currently using TrustZone M.
Okay, thanks.
There was a question there at the back.
Does this require some special annotations in order to call the functions?
Yeah, so it doesn't really require some special annotations. Instead, you use a slightly different function signature. So here's actually a small example of how this can look like. So we have this run function. We have a bunch of convoluted type parameters that we require here. But when you then actually want to call a function, so this is an example that I prepared, was called evil bool writer, that actually tries to write to a reference owned by Rust. Then you can just use our lib.dot signature here, and the remaining function arguments are effectively identical, except for that we are identical to what a regular FFI binding would expect, except that we also pass an additional access parameter here. Yeah. So if we run this right now, hopefully this actually is segmentation faults because this is not supposed to work. If we hadn't used encapsulated functions, this would have worked silently. And instead, if we then actually allocate memory in the foreign functions region, we can then safely write to that memory. But then we realize that this function writes a numeric value 2 to that Boolean. And when we then try to use this value, it's impossible to use this reference without actually validating it. And when we then do a call to validate, which is done here, we can see that it panics with the message invalid bool because that validation has failed.
Any more questions? There's a hand there. On the right side of the...
In the presentation, you mentioned using niches and how like C code could affect how Rust treats a tagged enum.
Right.
I don't understand how the validation could check that the enum tag got changed. Could you explain a bit more?
Sure, yeah. So the way this works is we don't check it on the enum tag itself. We check it on the value being retrieved from foreign memory and then copy it into Rust memory, where we would then insert it into an enum. So in fact, this example is actually is not only just contrived, but this actually doesn't really work on modern Rust because Rust does actually happen to, for any enum that has a sort of like a 1-bit representation, it inserts an additional AND instruction that we cannot otherwise explain other than this issue being so prevalent that Rust actually protects against the naive case of a 2-variant enum being communicated to C. So in fact, we reproduce this issue and actually get a segmentation fault when we extended this to a third variant and not use a bool but our own custom bool type. But what we do is we do it on retrieving this value, and then once Rust retrieves that value, for instance, our 3-variant pseudo bool, it assumes that value to be a valid instance of its type. It doesn't perform any additional checks, and actually, in fact, it moves it directly into the storage location of the discriminant of that resulting outer enum. And so it doesn't perform any checks at all. And we perform that check on loading the Boolean into Rust.
That makes sense. Thank you.
Is there a last question? No hands? There's one hand.
What if I'm a Rust library and I expose a CFFI and I have a C program that's calling into me? Can I use this mechanism in order to protect my objects from the application somehow corrupting the memory?
So that's quite an interesting question. We haven't looked at this before. There's some related academic work on that particular threat model. But those, I don't think that those actually explore the type infrastructure parts of this. So they're only concerned about memory safety. There is some related work that I could point you to offline, but they don't consider the type aspect. And while I guess there would be a way for us to port our contributions to those implementations, we haven't really looked into that at this point.
All right, let's thank Leon again for his great talk.
Thanks. Right, thanks so much. Appreciate it.
So it's time for a break again. And it's 30 minutes long, so we get back here at 15:50. And the next speaker after that will be Henk Oort. See you.
komt zo wel met water. Weet je wat het wel een beetje zeg maar als je hier achter gaat staan, dan sta je in principe in de boot. Maar je moet helemaal hier plekken. Maar als je hier maar dan denk ik hier achter is meer voor het licht. Ik sta nu uit. Dus hier achter staat dan. Ja, als je ongeveer kwart voor 4 dan ben je klaar. Ja, ik hoop dat want alles wat hier op staat gaat niet aan de livestream. Ja, precies.
Zet je ook nog water aan? Ja. Maar hoe meer water, hoe meer vreugde. Heb je dan niet gehad? Het is wel natuurlijk. Nee, dat is niet. Je moet eigenlijk niet laten komen. Ja. Ja.
TeachRS. Is it time? Yes, it's time. Everybody take a seat. I'll give you a couple of seconds. See, we're a little bit down on the punctuality now. Now we're getting later in the day, but that's all fine. Just hang in there a little bit, and then we'll get to drinks. I actually have something to say about drinks soon. That'll make people pay attention. All right, let's do this. Welcome back. I hope you enjoyed your break. I heard somebody complaining that there wasn't snacks, and there weren't any snacks. Some nodding happening. I want to thank the Rust Netherlands community sponsors, Technolution and Baseflow, also for making today possible. Before we get started with the next talk, I have some household things. We found keys. Set of keys, check if you still have your keys. If not, they may actually be at the reception desk. Another thing that we found is something that looks like a Game Boy but isn't a Game Boy, and then people were like, is it a Steam Deck? No. Is it a Nintendo Switch? No. It actually looks like a Game Boy but isn't. If that is something that you recognize as, oh, that's mine, then that's also at the reception desk. We're going to close the day with drinks. Drinks will be where lunch was, at the two areas over there. But there's an interesting twist. There's also drinks here at the front, and that'll be the only place where they serve alcohol. That's an important bit of information, I'm sure. No, get drinks there and then run outside and get a sunburn. It'll be great. Anyway, next up is Henk Oort. He works at Tweede Golf. I can't believe it. You're an embedded systems engineer, right?
Exactly.
I know that. Yeah. So his talk is Oxidizing Education because he created TeachRS, a modular, reusable Rust University course platform, which is totally awesome and super important.
Thank you.
Take it away.
Okay, so I hate to break it to you. Rust is great and all, but my employer doesn't want to use it. And there's like 0 jobs in Rust, right? Does this sound familiar? Well, as a community, we can change that. So my name's Hank. I hope you're having a great time at the RustNL conference so far. I wanted to share something about a project that I'm working on, which is about enabling people to teach Rust. And the talk is called Oxidizing Education. So let me introduce myself a bit. I'm a trainer and engineer at Tweede Golf, and I work on low-level bare metal firmware. I've also done a lot of web stuff. And apart from that, I give in-person trainings at external companies. And what I'm here to talk to you about, I'm a maintainer of teachers. So this talk is for everyone who would like to teach Rust to other people, or, well, want to get taught Rust at their university, or improve the overall Rust learning experience. So, what is oxidizing education? Well, I'm here at the Rust conference, right? So I'll assume you all know that oxidizing means introducing Rust in a project, right? And, well, what I think we should do is introduce Rust in education. And we as a community need to do this. So let's talk about this language, and particularly the things that stand out to me. So first off, Rust is a language that you can use for a lot of things. You can use it for, well, low-power bare metal firmware, or you can use it for reactive web front ends, and, well, almost everything in between. And that's really great. It's also, yeah, the memory safety stuff's out there, type safety. But on the front page of the Rust website, something really important is said. And it says there that Rust is a language that empowers everyone to build reliable and efficient software. So that means that Rust enables everyone to work on the cool projects, on the cool problems. You can work on embedded if you want using Rust, right? And I think that is something that is really important. So here's the bar chart that most of you probably have seen before. It's from Google, from an evaluation they did on their comprehensive Rust course. And what it shows here is that 2/3 of participants of that course felt confident writing Rust within 2 months. And so that shows that even though Rust is perceived as a language that is hard to learn, I think it's quite easy to get really good at Rust. And, well, you already have an idea why that is, right? It's because, well, Rust's feedback loop is so short. If something compiles, then it's very likely to be solid, to actually run well. And it gives you a great sense of robustness. Now, Rust is also Stack Overflow's most loved language for a while now, and that is a great advertisement to the language. I myself found about Rust that way. But there is more to this verdict. Because Stack Overflow measures the relative amount of people that have been using Rust in the current year and want to use it again in the next year. So, and the twist here is that not a lot of people are forced to do Rust by their employer. And that is because, well, there aren't a lot of Rust jobs out there just yet. And that is because we've got a bit of a chicken and egg situation going on with Rust. And it goes a bit like this. So this is a list of sentences that I hear very often at conferences and meetups. People say to me, well, Hank, Rust is great and all, but yeah, should I really invest in it? Because, well, there aren't a lot of Rust jobs out there, right? And I think that's because, well, companies are hesitant to adopt it. And companies, well, then are hesitant to adopt it because there's not a lot of experienced Rust developers out there. Not a lot of people can actually show they have written Rust for production. And, well, that's, of course, because there's not a lot of Rust jobs out there. And this is a cycle that we need to break. So, how are we going to do that? By oxidizing education, among other things, of course. So, let's talk about the current situation. Raise your hand if you've had C or C++ at your university. Wow. I already hoped it would be this way. So, and how many of you have been taught Rust at university? You're very lucky, and with very few. So, and well, I was pretty confident that this would happen because we can safely say that Rust in university is pretty uncommon. For instance, in the Netherlands, of about 22 universities, depends on how you count. One of them is kind of sort of flirting with Rust. I don't think they actually came through with it in the end. And another one is actually teaching Rust, which is great, but I also think that it's still exceptional. So, what can we do about this? So, there are a lot of things that we can do to improve this situation. And I feel that one of those things, and an important one of those things, is to enable people to teach Rust. To enable educators, but not only educators, to enable everyone to teach Rust, make it easy for them. And, well, that is where teachers comes in. So what's teachers? Teachers is a modular and reusable university course designed for in-person teaching. And by modular, I mean that you can pick and mix topics, and you can edit or add the material and add your own stuff if you want. And it's also reusable, which means that it is easy to just take and put into your own situation. It's structured like a code base. And you can compose tracks for different audiences or with different learning objectives. So a question that you may have, of course, is, don't we already have a lot of teaching material on Rust? And the answer, of course, is, yes, we do, which is awesome, right? Rust, I think, is really great at this. So we have the comprehensive Rust course that I mentioned just now. There's also, of course, the Rust programming language book. And there's the Crust of Rust YouTube series by John Yangset. However, all of those are either not meant for in-person teaching, or they're not modular, or not easy to adapt or to contribute to. And I would like for teachers to be all of those things. So can teachers do this themselves? Of course, it's their job, and, well, they're probably way better at it than I am. But teachers is meant to become a platform for, well, teachers to work together on creating this material and help each other out. And do people even want this? I think we do. We got a lot of stars on GitHub, and well, that's like Facebook likes to me. And our marketing team tells that our teachers' content that we post on social media gets by far most engagement. And, well, we post a lot of stuff on social media. So what is in there? So Teachers is a collection of material. There's slide decks, there's exercises, and on various Rust topics. And it's open source, it's public on GitHub, it's very permissively licensed, so yeah, you're welcome to use it. And Teachers consists of a number of tracks, which are comprised of modules. And a track could be something like Rust for Web, which teaches async Rust and then goes on to Rust web-specific stuff. Or you could think of, for instance, Rust for Systems, which teaches FFI or unsafe Rust. And then modules are divided up in units, which are again divided up in topics. And a topic could be send and sync or move semantics. And with a topic, a number of exercises may be related. And teachers is also reusable. As I said, it's structured like a real code base, so it's Git-friendly, it's GitHub-friendly as well. You can adapt it, you can contribute to it if you want. You can pick and mix the stuff that you need, and it's not even just for universities. You can use it at your own company as well if you want. So that summarizes what Teachers is right now, but I envision something greater for it. So currently, Teachers is a set of composable material, but I want to make Teachers a real platform where people can help each other out and work together on creating Rust-related teaching material. And it becomes one if it gets used by many teachers and students and developers. And this is where you come in. So how can you help? Well, first off, there's always room for improvement. There's exercises, examples that may need touching up that can be clarified, or may even need to be created. And if you come across such a thing, just go ahead, open a PR, and I'm happy to look at it. But furthermore, I love ideas. I'd love to create more tracks on different topics. For instance, we could create a track on embedded Rust. That would be lovely for me. Or we could create a track on Rust for data science. And, well, if you get enthusiastic about such a thing, I would love to work together on this. You can go ahead, open an issue on the repo, or, well, find me somewhere in this place. And most importantly, tell your friends. If you're a student, tell your teachers, and if you're a teacher, well, tell your colleagues. Thanks.
All right.
This QR code points to the repo, if you like.
So we have time for some questions. I see a hand there. There comes the mic running.
Oh, there, yeah. So this is kind of a Dutch language thing, which is always annoying. If you say university, do you mean also universities of applied sciences? So that's HBO in Dutch, or do you mainly target universities as in proper universities, quote unquote?
Yeah, I mean, I wouldn't say there's a real difference for, well, in this case. So, yeah, definitely use it at your University of Applied Sciences,
yes.
Whatever
Thank
that
you.
means.
There in the back, in the front too.
Hi, so I'm actually in charge of watching the live stream, but this isn't a question from the live stream, it's a question from me. I was just sort of wondering, how is TeachRS different from something like Rustlings?
Well, it's very different because, well, the main difference in this case lies in the fact that it's designed for in-person teaching. So it is meant for, well, someone like me to present it to a room like this one, and by coaching people on the exercises, for instance, where Rustlings is something that you can install on your machine and it will guide you through Rust. And there's preferences, right? So for a lot of people, Rustlings works perfectly, and I think that's great. But for other people, other learning methods work better, and one of those methods could be in-person teaching. So that is where Teachers is aimed at.
I see. Thank you so much. We also have one question from the live stream, which is, how would you go about making a new track?
Yeah, so I would say 90% of the work is in designing the learning path. So I have tried to make this really easy. So for instance, if you would go for the embedded Rust track, for instance, I think you should introduce the Rust language. You cannot assume that a lot of people already know Rust, or well, maybe in your situation you can, but it depends. And then you add some modules which introduce, for instance, the Rust embedded ecosystem with all those topics. And so it's I would say, first off, start by opening an issue and, well, share your ideas, and we can talk on this. And yeah, then it's just a matter of forking the repo and creating some files and text and designing exercises. And yeah, I admit that is a lot of work, but I would also give you a hand with this. I really would like to collaborate with other people on this.
So there's 2 people there.
What's your opinion about Rust as a first language to teach programming?
I'm not sure. I actually was working on an experiment with this because there's something to say for it, right? Rust gives you the guardrails, it gives you the short feedback loop. However, I've done some trainings and with different audiences, and I feel dropping all of the Rust concepts that you need to actually go about creating something and then, well, get a bit of dopamine back from it. Yeah, you really have to dig through a lot before you can get started. However, that said, I think that it is really improving in the last couple of years. And, well, maybe it might turn out that at some point Rust will become a great language, a great first language.
Hi, thanks for the talk. So after a few years, I have finally managed to convince my computer science faculty to let me teach Rust at our university starting next semester. But I wanted to ask you if you have some opinions or maybe experience. Do you think that it's better to teach a subject about Rust specifically, like have a subject, you know, the Rust programming language, or maybe have like subject that focuses on some specific domain and just use Rust as a language to implement the domain, like, I don't know, data science or pretty much anything?
Well, it kind of depends on your goal. So if your goal is to actually introduce Rust in your university, I would say use it as a vehicle to teach another subject, for instance, or it could be operating systems or something, or embedded. But well, you've already managed to get Rust in, right? And in that case, I would say, yeah, go ahead, introduce the language itself, go with the high-level concepts, and then if you want to teach, for instance, data structures, you can use all this prior knowledge, and you'll have much better time.
Okay, thank you.
Just don't let them do linked lists, right?
Yeah, or maybe do, and well.
So we still have time for questions. I remember someone had raised their hand there. Yeah, there's it.
Thank you. So I think a lot of difficulty in especially bachelor programs to find, to introduce Rust is finding a place, like finding the time to introduce it to students. Mm-hmm. Because as you said, as a first programming language, it's not really common. But there's like a lot of content. So for example, people should know C just because so many like old systems still use C. So do you have, as for the topic of oxidizing education, do you have an idea of well within a program this should kind of integrate?
Can you repeat the question, please?
So where would you imagine this like teachers to be used within an entire program?
Right, yeah, so going back to my experience when first getting taught programming, I actually got taught C as a first language on university. And well, C wasn't the hard part. It was trying to manage to get a click in your head to actually divide up problems in sub-problems and then, well, divide and conquer, right? And I think a lot of people will recognize this. And you have to get through that phase, I'd say, before getting into the well, really deep stuff with Rust. Be able to, well, get that click first to divide your problem up in sub-problems and then solve them, and then go ahead, you know, do pointer arithmetic or something, or, well, and then shoot yourself in the foot with Rust. And so I think that click needs to happen before starting out with Rust, but then, yeah, I think it's a great language to introduce concepts like stack and heap, for instance, too. Yeah.
All right. This was. We still have one time for one more question. There's a hand here. Yeah.
Thanks for the talk. Do you think that this could also be a good fit for in-company training, or is it really too much full-time weeks of education course material for companies?
I would say yes. I do it myself. So yeah, I'm definitely using this material to teach Rust at other companies, but your mileage may vary. It really does depend on the target audience, if you can go through the whole language introduction in one day or not. That really depends. So first, get a good idea of your audience, and then, well, either go fast or go slow. But I think definitely you can use this content. Yeah.
Would be an interesting thing to see if there's a relevant subset of the modules.
Yeah, definitely. Yeah, yeah. If you need any help with that, just hit me up. Thanks.
Excellent. So thank you very much.
Thank you.
So next up is James Munns. He's a Rust consultant at his own company, One Variable. He's also one of the creators of Nem OS. Not sure if I'm saying that, NEMOS. And he created Postcard, so he's going to tell us about that. I think we was all lucky you gave this morning a workshop, so we are getting the like warmed up version.
Yeah. Thank you.
Well, take it on.
Cool. So I'll stand about here. I'm not in the way. Sound good? Cool. All right, I have a timer because I have 125 slides and we've got 30 minutes. So I've got marks to hit. So stick with me on this. So let's go to the timer, and we are, let's make sure this works. Yeah, great. Yeah, so this is Postcard, an unreasonably effective tool for machine-to-machine communication. So I'm James. I hang out a lot in the embedded scene. I've been involved in Rust for a while. If you've hung out in any of the embedded rooms or somewhere else, I'm terminally online. So you might have talked to me at some point, or I might have helped you with some problem, but these days I work for my company, One Variable. I do consulting. I do a lot of helping teams either go from one really excited Rust developer to 5 or 10 functional team members, or people who are looking to build their next project and need it right now, or yesterday, if possible. So I do consulting, so if that's the kind of thing you would like help with, feel free to reach out. So I work on embedded systems, which is a totally worthless term that doesn't mean anything, because it's everything from the tiniest system you can imagine to huge things that are all around you. It covers everything, but the way I like to generally describe it is computers you don't necessarily sit in front of. Now, this could be anything from the key fob or the car behind it, or giant expensive scientific equipment like something like this, that you would think as maybe digital, but not like a computer or a phone that you sit in front of. They do something specific well, hopefully. Now, one of my most common tasks, either when I get brought in or for the kind of projects that I do myself, is to help computers talk to other computers, which sounds very straightforward, but computers are special little devices sometimes. Sometimes when I get brought in, all the decisions are made. They say, it's wired up like this, it speaks like this, we need optimization, we need something, we need it to work a little differently in some cases. And other times it's a paralyzing void of options, because there might be nothing there, and when they bring you in, it's your job to stare into the void. So I'd like you all to stare into the void of me, of being brought into a brand new project where the entire plan so far is this napkin sketch. You've got a computer talking over USB to a much smaller computer, a microcontroller unit, something itty bitty that's going to be talking to your much bigger computer for whatever reason you'd like to be doing that. Oh, and by the way, the demo's in a week, and they've got investors there, and it has to work, at least for the 20 minutes that the CEO is going to be on stage pressing the buttons that you are soldering today. So you better start quick. Now, the first blessing is that, just from the niche that I'm in, most of the customers that reach out to me are already using Rust, or have already decided that Rust is what they would like to be using. So they're using Rust on a PC, on their microcontroller, on the phone, on the server, usually on both sides of this conversation that we're talking about today. And this makes everything so much easier because, surprisingly, you can share a lot of code from an itty-bitty microcontroller with 8 kilobytes of RAM with some hyperscaler server that's in the cloud, or the MacBook that you have that has 64 gigabytes of RAM on your desk in front of you. And the second blessing is we have Serday. So you've probably used, if you've used Rust, you've probably run into Serday somewhere. It's a library for serializing and deserializing data. But the special trick is that it doesn't just work on your desktops and servers, it also works on microcontrollers. Now, Serday is about, I want to put Rust data on the wire. We are taking Rust data types that live in memory that the compiler put together for you very nicely, and we'd like to get it from here to over there. And that means putting it into some format that we can send over some kind of wire or radio. We have a type like this, an accelerometer reading. It has 3 fields, X, Y, and Z. They are signed. This is a Rust data type. It doesn't exist on the wire. But if we slap this on top of it, all of a sudden it goes on the wire, which is tremendously convenient. We've now solved the problem, but only halfway, because Serday is actually split into 2 parts. The front end, which thinks about Rust data, and the other half, which is the data format. You might think of it as JSON or TOML or YAML or whatever format that you're using, but Serday is the front end, and the data format crates are the back end. That's actually what we put on the wire. And whenever I say on the wire from now on, I mean Ethernet packets, serial ports, wireless radios, Wi-Fi, any of those things. That's the wire to me. Now, the problem is embedded systems don't always have nice things like operating systems or allocators. They are itty-bitty little friends who have so little. But luckily, Rust helps you handle this with no standard. It's a version of the compiler that lets you skip those things in the situations you need them for. Now, in 2019, there weren't very many data formats that worked with no standard. There are a couple. I didn't love any of them. So I came up with a crate called Postcard. Postcard is a library that is a data format that works with Serday that's designed to work anywhere. Now, for one of the few times in my life that wasn't a customer project, I actually did the right thing and sat down and wrote down what I was supposed to be doing. What do I want this library to be? And lightly edited, it looks something like this. I had to remind myself that we are working for embedded systems first. It should run everywhere, but it should be specifically for embedded systems. It has to work no matter how small your chip is. 16 megahertz CPU with 8K of RAM should be no problem. And it should be as easy to use as Serday, as any other Serday format. As easy as you slap Serday JSON into a project and start slinging JSON over packets, it should be that easy no matter how small your chip is. And when you use it on your PC and on your microcontroller, it should be the same. It should not require special, painful, annoying code because I'm an embedded developer and I don't want to make my own job harder. And it has to be resource efficient. I've said we've got tiny little CPUs, tiny RAM, very little code size, and we have a lot to do as developers. That's a resource that needs to be managed. So I decided that these 5 in this order were how I was going to prioritize my work towards this. And like I said, I mentioned Wi-Fi, serial ports, all of these things. There was always going to be, embedded is full of, oh, well, we need it just a little different. It has to be a little special. So I knew that there was always going to have to be a little room for leverage there. So I made the format as dumb as I could, both because I'm not particularly creative, but also it makes it easier to deal with later. The format is probably about what you expect of, I have Rust data and I would like it to be in bytes. It probably works not very far from how you would sit down and come up with that right now in the next 5 minutes. It also doesn't do any bit packing trickery. It only deals with things at a byte level resolution. And this is because your desktop CPU might have some very clever instructions for doing very fancy things. That may not exist at all on the microcontroller. So you want to avoid anything that could cause serialization or deserialization to slow down to a crawl. And I come from a C background. I was taught C in university. You'd be surprised how many production systems out there, particularly embedded ones, just transmute structs or pointer casting in C from a struct to bytes and then calling memcopy on those bytes, which you can do. You can do it well, but it's don't do it lightly. There's a lot of gotchas, and it will subtly break, and then you'll spend multiple weeks debugging it, like I did at multiple of my customers, which is a very frustrating experience that you were talking between an 8 and a 16-bit microcontroller, and it turns out endianness works differently sometimes. Now, Postcard is a non-self-describing format. That means it sends the raw values on the wire, nothing more. There's nothing about type names, nothing about field names, nothing like this. There are no safety rails. There is the data as it exists on the wire. Partially, this is for efficiency reasons. We don't want to be sending and receiving more than we have to, but also, why spend extra effort if your computer and your microcontroller agree on what these types are? Why repeat yourself over the wire? You're going to be spending way too much time sending data that's not actually useful to either side, usually. So because also I started this in 2019 and not in 1974, where big endian computers are the standard, your microcontroller and your desktop and your server are probably all little endian machines, so we buck the standard network order trend of putting everything big endian, because why waste the extra cycles swapping everything on both sides? When it comes down to putting that data on the wire, it might work like you think. Structs, if you have fields A, B, and C, guess what order they go on the wire? A, B, and C. If you have tuples, they go 0, 1, 2. They just go in the order they are defined as the types. Slices get prefixed with their length, so you know how many things, and then they get serialized on the wire as you would if you were serializing just that one thing. Enums are prefixed by their discriminant, so you know I have this variant of the enum and the data that goes in that field. I told you it's been pretty obvious of how this design went. The one catch was originally slice lengths and discriminants were varants. If you've used gRPC or protobuf, you know variable size integers, or if you work in the compiler, LEB64 or something like that. We want integers to only take up as much space as they need because, for example, if you send a slice of things over the wire, how often are you sending 2 to the 32nd items? You're probably more sending 4 items most of the time. So why take up 4 bytes for that when 1 byte will do? Today, we've actually made all integers varants for portability reasons that I won't get into. But and I mentioned that need to customize down to the last little bit. I provided a system called flavors that are stackable combinators on Saturday. They work a lot like iterator chains. When you're receiving the bytes in and you want to deserialize them, it's kind of a hook point where you can modify those bytes before they do the deserialization. So if you have checksumming or compressing or some other encoding, you can do that while you're serializing and deserializing instead of having to do it as discrete steps. Usually this saves you some working memory as well. With all of these customizable flavors, I will tell you there are some generics involved, and generics are not always the most pleasant thing to have on your API surface, but for most of the common ones, we have helper functions that hide it, which means changing the entire way that the data is encoded is as simple as going postcard to slice, Postcard 2-slice cobs, and now it is an entirely different wire format that helps you on serial ports tell where one packet starts and that packet ends. So 2019 to 2022, I used Postcard a lot. It was in a lot of my projects. And it turns out so did a lot of other people. It's become somewhat of a ubiquitous standard in the embedded Rust world to use Postcard because it works well for that domain. And about that time, I realized I was so worried about breaking changes and things like that that, you know, it's time to make it 1.0. So for 1.0, I cleaned up the last portability issues that have to do with how Serday deals with U sizes and I size and the fact that it doesn't tell you that it's doing that, which makes things not work so well on 32-bit and 64-bit processors. And I actually wrote a stable wire format, a document that's not coupled to Serday or Rust in particular at all, that says this is how this data is encoded on the wire, because someday there might be something other than Serday, or I might want to use a language other than Rust that uses this encoding. So 2022 and 2024, I kept using Postcard a lot, ton of customer projects, started popping up in even non-embedded places like Bevy or Wasmtime or, let's see, there's some other ones, but people kept using it to shove stuff from memory into caches or on-disk file formats or blobs of data in their database and things like that, because it just works pretty well and it goes pretty quick. I guarantee you if it works on that tiny little microcontroller, it's going to work on your server. And it got to the point where basically every customer project I was doing, I was using Postcard somehow in one way or another. But I had a problem. And it turns out that if you have good tools that you like using, sometimes you use them too far. And you start using them for things that they're not really supposed to be used for, just because they're so pleasant to use. So let's look at that stack from my computer over a serial port or USB to something like that. We've got our physical layer. This is where electrons move back and forth or radio waves move back and forth. We're thinking in either bits or bytes, you know, data on the wire, literally on the wire. Now, one layer up from that, we have to deal with framing. This is something where we turn either bits into bytes or bytes into frames, where we turn a stream of bytes into a stream of packets. If you're using Wi-Fi or UDP or USB, this comes as part of the protocol. You don't have to do anything. For serial ports, it's a stream of bytes forever. You've got to turn those into messages. This is where those flavors come in. Postcard lets you do that out of the box. The encoding layer is literally Postcard. It is encoding and decoding the data, or serializing and deserializing the data. Great. And then I got to my customer projects where I had to write application logic. I had to actually make it do something, because we're not just moving around these bytes for fun. We want to affect change from here to there. Now, like I said, Postcard handled all this stuff really well. You either had it out of the box, it gave you sort of like a polyfill to let you deal with that, and the encoding it had on lock. But this part for non-trivial projects actually was feeling less pleasant than I had wanted it to be. Particularly when you say, I'm not just sending one kind of data this way and another kind of data this way. I have a lot of different messages that I send back and forth, and I need to know how to deal with that. And it turns out that every project required a lot of custom work. It wasn't necessarily hard work, but tedious work. And as developers, we kind of hate repeated tedious work. You go, there's got to be something better. And honestly, usually it was a lot of copy and pasting. I would have an open source project, and I'd copy that to the next open source project, or I'd take my most recent open source project and copy and paste that into a customer's project, because I had a rhythm down. It wasn't an abstraction, because I was copying and pasting the same 3-4 files in different projects every single time. But I couldn't figure out how to abstract this. Every project was different. I had different behaviors. I didn't know how to make this consistent between them. And this part was hard. Until I realized that what this diagram was missing is a defined protocol layer. Because at the end of the day, Postcard is not a protocol crate, it's an encoding crate. And I had gotten complacent because I was so used to it filling in all those gaps around the communication that I had found that I kept using it for that. But it turns out I was using it beyond its means. Because the application is how these systems behave, your business logic, what they're supposed to do that's unique to that project. And a protocol is how these two systems communicate with each other. What behaviors do they expect from each other when it comes to passing data back and forth? And it turns out I was reinventing a bespoke protocol on every single project that I was doing. It was tremendously convenient and easy, but that was not really the best way to be conducting myself on these projects. And the really painful part is I had to do it every single time. Even very similar projects, I had to copy and paste the same chunk of code, getting bytes off the wire, framing it, deserializing it, figure out what to do with it, usually deserializing into a big enum coming in, match statement out, and then I respond, put it in a big enum going that way, and it was just kind of clunky and gross. But what if there was a protocol that was available out of the box, the same way that there's encoding or framing available out of the box? Because this part was easy because Postcard handled it for me. And if we had a protocol layer where someone's doing that work for me, or me yesterday is doing that work for me tomorrow, then that part becomes easy. This application layer stuff's still custom, but that's life. My customers are not all working on the same thing. My projects are not always on the same thing. That's always custom. It's going to be life. That's what I should get brought in to do. So meet Postcard RPC, which is a protocol on top of Postcard. So I said that a protocol layer is responsible for some behavior, some action, some way of communicating. So what ways of communicating does Postcard RPC have? Well, I've defined that you do have a client and a server role. And again, I'm not very innovative. A lot of these are going to sound very similar to other things that you've dealt with in your professional careers. Because when you define the roles like client and server, it makes other expectations more clear. You have your PC, and this is going to sound a little upside down to some people, but your big, giant 64 gigabytes of RAM PC is the client, and your itty-bitty little microcontroller is your server. Because if you think about it, your computer's asking your microcontroller to spin a motor for you, to read a sensor for you, to set the LEDs a certain way for you. So it's the server in this setup. Now, RPC is a term that means remote procedure call. You've probably heard of gRPC or JSON RPC. It's a common term in the industry, especially if you're talking with things over the network. And what this really means fundamentally is that we have a request and a response, and every request gets a response. The client initiates, the client asks. If you think about making a web request, you make a request to a server, and the server gives you back a response. It goes like this every single time, and they are always paired together, as long as nothing's gone wrong. And the reason why we call it a remote procedure call is because procedure is just a fancy name for a function, and you have a function that looks a lot like async function procedure that takes a request and gives a response. And you close your eyes and forget that there's a network in between these two, because when you model it as a black box, it just looks surprisingly like a function or a remote procedure call. The other behavior it has is topics or streaming and things like that. This is the kind of stuff you would use WebSockets for. Either I have a sensor that's pushing out data every 5 milliseconds, and I don't want to be asking for that data over and 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 over. You get the point. And doubling the amount of packets I have to send, you say just start sending the data. The word topic comes from, if anyone's used MQTT, it's a pub-sub-based protocol, and I just kind of stole the name because it made sense. Or the opposite, notifications. If you are waiting for a button to be pressed, you don't want to be asking every 10 milliseconds, is it pressed yet? Is it pressed yet? Is it pressed yet? Is it pressed? You go, just tell me when the button has been pressed. And this doesn't fit into that RPC thing, so it turns out with these two primitives, you can cover a tremendous amount of functionality. Topics are also special because instead of just being initiated in one way and responded, they can go either direction. You can stream data to your microcontroller, or your microcontroller can stream data to you. But you never get to respond to these messages. It's a one-way broadcast. So, all like this or all like that. So, how does Postcard RPC do that? So, I said Postcard puts nothing extra on the wire. It just puts your data. So I've added one extra thing at the front. It gets a header with 2 different fields. The first is a sequence number. This is just a way of uniquely identifying what message this is, or this is the first or 10th or 10,000th message I've sent. And this is because our microcontrollers, like your big servers, sometimes take different times to process different requests. If I say, start spinning up the motor and let me know when it hits this RPM, that might take longer than, what's your version number? So we give it a unique ID, every way going that way, so we know which response goes with which request. And the other thing they get is a unique key. And this is a way of identifying what kind of message it is. So I've mentioned Postcard, again, does not send anything about schemas and things like that. It sees bag of bytes and tries to deserialize it to the type you tell it. But that doesn't help us if we are sending it a lot of different types of data. So the way that we do this is we take a path or the URI or the endpoint that we're talking about, and we hash that, and then we hash the schema of a message. We actually, at compile time, have a proc macro schema that expands to the schema of the message on the wire, hashes that, including all the fields and types and things like that, and combined with the path, you get a unique key that uniquely represents that request or that response. For now, keys are 8 bytes, but this is just because it was big enough to avoid collisions for me and not too big to be extra overhead. And these keys are generated at compile time, because it'd be very silly to be doing this hashing at runtime. So I wrote a compile or const function that can do FNV1A hashing. So you just do this once, the compiler saves it, and it's just a bag of 8 bytes that you throw at the top of every message. And now that the protocol is standard, we can begin providing reusable protocol code. On the host side with USB, we've got a lovely crate called NUSB that exposes the low-layer guts of USB in a handy async format. And on the embedded side, we've got a crate like Embassy USB, which is a USB stack that works on basically any microcontroller with USB, whether it's from STM or Nordic or Raspberry Pi. So in this stack, now I can give you a library for that host client, and I can give you a library for that target server, which means now I've cut all of that boilerplate out, and you just have to worry about your application up there. So what does the code look like? Well, something that I did before, but I've continued doing, is when you've got your microcontroller project, that's a binary crate, and you've got your desktop project, that's a binary crate, they need to share what kind of types they're going to be sending back and forth. So you usually have a crate that has nothing but data types in it. Normal sort of looking stuff, derive, serialize, deserialize, that extra schema derive that's on there, not a lot of extra work. So you might say, I'm going to tell you to go to sleep for a certain amount of time. And then I'm going to expect you to respond back to me exactly how long you slept, because maybe you slept a little less, a little bit more. So we have this endpoint macro that says we're going to define the sleep endpoint with the request of sleep, the response of sleep done, and the path is this sleep. The reason why we have this path there is because you might, especially for common types like integers or whatever, you might have a bunch of endpoints that give an integer and get back an integer, so we need a way of uniquely telling the difference between them. We just hash it, so it looks a lot like paths or URIs or endpoints on web requests, but it's just going for style. Now, what that macro does is it generates that struct and it fills out this trait implementation. I don't have a good name for this, maybe a lot of smart Rust people in the room. I've just been calling these metadata traits. It's a convenient way of coupling types and consts together. So this endpoint has a specific request type, a response type, the path value, and then at const time we generate those keys. So that's all that macro does, and it just bundles them into one name because they always travel together. Similarly for topics, for those broadcasting things, we have a type, serialize, deserialize schema. We declare a topic, same kind of thing. We get a trait, this metadata trait that has a type and some consts on it. So on the embedded side, instead of having to write a lot of code for serializing, deserializing, basically doing all the plumbing that we have to do, instead, we can just write these function handlers. And if you've used Rocket or other web crates like this is going to look a lot like those endpoint handlers you write in those crates. You have a function that takes some context, we get the header that we were talking about, and the request. So this first one describes a request that takes nothing and gives back a U64. The second one's an async function that gets a single lead struct and gives back some kind of result. We also have the ability to say, we're going to spawn a whole task just to handle this, because maybe that one's going to take a while, so we don't want to wait for that answer to be ready before we go on to process more information. And then at the top of our microcontroller code, we can define the routing or dispatching in one place in our code. This is a big macro, don't worry about it, but because we're working with a lot of different chips that have different USB drivers, some of them are single core, some of them are multi-core, this is just some details you need to tell us how to handle that. And then you get this little match statement looking block that just says when you get this endpoint request, call that function. This one, that function. This one, that function. Instead of like a proc macro like you would in Rocket, we just put all the routing in one place. And you'll notice that there's different flavors of them. Blocking, async, or spawn. And that's, do we call a blocking function, an async function, or do we spawn a whole async task to handle this? And because all of these endpoints have the types associated with them, we can generate all the code for the request and response because we know the types at compile time. And on the PC side, you don't have to write your own plumbing code either. You can make an endpoint request that looks like this. You connect to some device with the product stream OV-twin, and then this is all it takes to send a response over raw USB, have it be serialized, have it go to your microcontroller, wait for your microcontroller to respond, deserialize the response, and see if it went well. Send, and wait for the response. And you give it that ping endpoint because that's all the data it needs to know exactly what kind of types over the wire we're going to use. Same, if you are on the desktop and you want to subscribe to that stream of sensor data, we've got a method for that. We've got client.subscribe. You give it that topic metadata, and it goes, I know exactly what I'm going to be listening for. You tell it, buffer up to 8 items, and it gives you an interface that looks like a Tokyo channel, basically. You can just await receiving the next message, and you'll get it every time it comes in. So we've separated our concerns. We now have the ability to not specify this in every project, to provide reusable code on both sides, and to make having that whole conversation just as easy as serializing and deserializing the data was. Because Postcard is about making data go from here to there effortless, and Postcard RPC is about having that conversation be as effortless as possible. Because no matter how you connect to your device, whether it's USB, serial port, Ethernet, whatever, they're never more than a postcard away. Thank you.
That was a very nice presentation. Thank you very much. And I'm sure there are questions. Who wants to go first? I see a hand there over there.
Thanks for your talk. Given that you just encode stuff in order of the properties, how do you handle changing your structures and then deploying them one at a time on both ends?
You don't. Yeah, that's a very good question, and that's one of those things that schema evolution is one of those challenges that I've faced over time, particularly because firmware devices get updated on a way different scale than servers or desktop applications do. Postcard RPC takes the most conservative choice here. You change anything about that struct, the name of the field, the ordering, things like that, that hash changes, which means then if you make that request with the wrong data type, it says, I have no idea what you're talking about, because it just knows that hash value there. So it doesn't help you with that, but it does help you from the foot gun that you might misinterpret that message. And my opinion on that is generally that if you have a desktop or a server, have all versions of the packet and figure out which one you should be using, and have maybe one version ID that never changes, but it will never misunderstand that, at least in Postcard RPC. Postcard, you just don't, or otherwise it might have problems. Yep.
The next question is over there.
I was wondering how configurable this crate is. For example, I have an application I do with students where using these sequence numbers and sending back responses is just something we don't want and don't want to pay for. Can you strip parts out of this, or are you getting the full package always?
Right now, Postcard RPC is very opinionated. It says you get the sequence number, you get the header. You can take the vibes of this and customize it as you like. Not going to bug me. I want to avoid the ability, especially in embedded, we had the habit of making everything tunable, which made the UX horrific because you got 9 generic parameters and you've got a compile time feature. So the answer is no. As I go on, I will probably eventually hope to formalize this protocol the same way that I did the wire format of that and sort of make it more specified. And for there, feel free to take the ideas and run with it. But for now, I'm saying this is any color you want as long as it's black, kind of.
There you go.
Yeah, so thank you, James, for a great talk. You kind of mentioned that Postcard RPC could fit in the same place as MQTT, right? So what if I wanted to talk to a Postcard RPC broker, if that's your term, from an application that's written on Sever, for instance?
Yeah, right now, again, generally you can't. It relies real hard on Serday for the encoding information. Excuse me. You could always FFI and things like that, but as I mentioned, I'm primarily focused on Rust to Rust communication today. Like I said, I hope that Postcard will outlive Serday and that it could use whatever is different than that, or there's certainly cases where I would love to have a code gen tool for C or Python or C# and things like that, because not all of my customers use Rust for all of their parts of their entire stack. So the answer is, if this proves itself out well and I learn from this and it goes fairly well, I'm interested in that. But also I need to be careful not to overstep, because Postcard RPC also does not handle addressing and things like that. It assumes either you have point-to-point or you're handling that. So maybe the next step is Postcard NetStack, I guess. But MQTT has quite a few components in it for both routing and communication and things like that, or ignoring it because it's pub sub and you have a broker that you're talking to. So the answer is you could probably build something in that shape, particularly those two primitives of endpoints and topics composed together really well. Like sometimes you have an endpoint to start streaming on a topic, or an endpoint to stop streaming on a topic and things like that. So maybe, but also it's more peer-to-peer than broadcast right now. But that's interesting, and I'd love to talk to about it.
Thank you.
Got a question over there? I will want to know about your step counter later.
Hi, so I was wondering, does the proc macro check if the key is unique over the entire application? Or can you accidentally, by specifying the same path and the same type, get a collision?
So it's a declarative macro, not a proc macro. But I can tell you that define dispatch macro, this this essentially just boils down into a big match statement of the 8 bytes on there. And I put in the expanded code deny unreachable match arms. So if you either accidentally put the same endpoint twice or somehow get a hash collision on one of these, it won't compile unless you disable the deny. But I have deny unreachable match arms, so you'll get a compile error, at least in this implementation of it today. Yeah, and that's part of the reason why I want to have that whole thing in one blob, is because it gives you that sort of whole program visibility to say, these are the endpoints that I'm talking about. So you only catch it when you build your server, but your server will refuse to have totally masked away endpoints.
All right. Any other questions? Oh, over there. Ooh, 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 ooh. Eager arms going up.
Thank you for the talk. My question is quite short. Is it canonical format, like how it serializes hash maps?
Sorry, could you repeat that?
How, will 2 different PCs with 2 different programs running in RAM with the same keys in hash map produce the same binary, or it depends on the seed?
Yeah, it's deterministic. It uses specifically FNV1A, and the way that I do it is essentially, it's deterministic. So whether you're compiling for a microcontroller or whatever, that hashing that gives you the key is totally deterministic. Because it basically recurses through the schema in a specific way, and it hashes the text in a certain way. So it is deterministic. Does that answer your question? Cool.
Okay, thanks. I have a question. In your stack, you have Postcard as a wire format. Then you have a Postcard RPC for procedures. But what do you use for frames, basically? When you have a TCP stream or Bluetooth stream, how do you distinguish bytes into messages?
Yeah, so Postcard itself has a flavor called COBS, which is a secret weapon from the days of dial-up. And it's a neat trick of you use zeros or null bytes as the frame delimiter, and it's a way of encoding messages so that none of the data bytes are 0. So even if you were to send a packet full of zeros, what it does is it essentially makes a linked list between all the zeros in the message that terminates at the frame header. And it's tremendously performant, and it's, like I said, it's from the days of telephone network framing. It's called COBS, Consistent Overhead Byte Stuffing. So Postcard has that as a flavor. I have one variant for USB. We don't need that because USB has its own built-in framing. But I do have a version of Postcard RPC that works over UARTs, like raw serial ports. So it uses Tokyo serial, puts Cobb's framing in front of that, and then on the other side. I don't have the pretty server macro working on anything but USB right now, but that's just a limitation of what I've coded so far. So Cobb's is my go-to answer, but there's a lot of other ways to do it. But Cobb's is my favorite because it's fairly efficient, resilient, and with very little overhead, and not a lot of room to mess up. So I really like it. And Postcard has a ton of helper functions and structs and types that help you do Cobb's with Postcard, because everyone who's using it over a UART or USB serial is basically using Cobb's with Postcard.
All right. Final question?
There's
Nobody
one
else?
over there, so.
Yeah? Final question. There we go.
I'll be here for all of tomorrow and through the Impl days, if you'll, or the Unconf, if you'll be here. So definitely feel free to come grab me.
So I use Postcard for serializing data for Dioxys, and Postcard doesn't support all tags of Surday. So I'm wondering if you think those more tags would be possible to support for Postcard, or if it is something that a public library that uses Surday should keep in mind when deriving the data format.
Yeah, so there's a number of, Serday has its own customization fields. If you've ever used like Serday flatten or Serday rename and things like that, the way that Serday is implemented, it doesn't bring all of that information down to non-self-describing formats. It sort of just confuses the serializer and deserializer. I have an open issue on the Serday repo asking how to handle this, but my answer unfortunately is just don't use those. And that sometimes is painful when you have something that's like taking JSON messages in and you want to then turn around and reserialize that as Postcard and the other way out. And unfortunately right now the only answer I have is to duplicate those types without those, which is really unsatisfying. But I have an open issue because it does bite people sometimes when you use flatten or other attributes like that. And unfortunately I haven't gotten a response back of how to handle that as a data format writer. So I'd love for there to be one, but I have a feeling it'd probably end up having to be a breaking change to Serday, which I don't know when or if would happen.
Okay, thank you.
Yeah, thank you. It's definitely a common pain point, and I've had other people run into that too.
All right. Thank you very much.
Thank you. Thank you so much.
And with that, we concluded the final talk of the day. Yeah, I think it was an absolutely amazing day. I hope you all enjoyed it. And now I am once again in the way between you and drinks with a couple of household messages. So, boats will go back from here to Delft Station. One will go back directly, leaving at 6 o'clock sharp. The other will leave at 6:10. And the second boat will make a tour through the city canals, and it will last an hour and 15 minutes. So if you want to take like a sunny ride through beautiful Delft, it's actually a really nice city, I totally recommend that. Tomorrow there will be boats again, and the boats will depart from the station at 8:20 and 8:35, bring you from the station directly here. That's the household messages, yeah. And then I want to take this opportunity to thank all of the volunteers who made this day work. Yeah. And actually, I want to be specific about this. So thank you, Erik, Jonathan, Laura, Tertz, Araf, Bram, Goran, the other Jonathan, Lisette, Lucas, Reinoud, Vivian, Wouter, Erwin, Dirk-Jan, Anna from the Red Dress Effect, who's the event organizer, and all of the lovely people from Lijmen Cultuur. Thank you. Give them a big hand once again. Thank you. And I am your humble host, Alex Band, together with Adolfo. Come on up here. You're great, thank you. Thank you. All right, now you get to go and run out and get drinks. Yay! See you all tomorrow! Thanks, man. Ja, dat weet ik. ik weet niet meer wie dat nou was. Die zei, ik weet niet